Hello, Nikita.
Uh, Sir,
Yes.
this is Harita.
Yeah, Harita.
So I just want to know how it's done. I mean, will there be a questionnaire session after each talk?
Yeah, I mean, participants are encouraged to talk to their friends while they are presenting.
Yeah.
And yeah, of course, at the end also, we'll ask them briefly.
Okay. Okay. Okay.
So actually, should we ask the participants to try their presentations, like at least the first group, Bhavtarini? First group of people should let us know who is presenting from their group, and then
Sir,
yes,
I'm Darshini, sir, from the
yeah,
group of Bhavatarani.
yeah.
I'm going to present the slide, sir.
Okay, so we should allow you, yeah, to present slides.
Yes, sir.
So that host can do actually.
Okay.
Sir, I've given permission for all the participants to share their screens.
Okay, okay.
Yeah.
So
So I hope there won't be any confusions.
okay, thanks. So Darshini, you can at least once try sharing your screen.
Okay, sir.
Nikita, you got the details, right?
Yes, I got it.
Yeah.
Thanks.
So there is one group of 5 people and they have split into 2 parts. So they will be doing the distributive lattices and nested ASCII theorem, both of them. The cardinal arithmetic one is not happening.
Oh, I see. Okay. So so that group is split in two and they will be presenting on the same topic or one on
No,
distributive?
different. So I think Nikesh will be presenting on distributive lattices and uh, Muthukumar, yeah, perhaps Muthukumar is going to present on nested
Okay.
ASCII theorem.
Okay.
Sir, Chaitanya will present on Nashta Taski.
Okay, Chaitanya will do it. Okay, no problem.
Darshini, are you facing some difficulty in sharing your screen?
No, ma'am, I'll do it, ma'am.
Okay.
Ma'am, is it sharing, ma'am?
Yes, we can see something happening, but we can't see your slides. Right, Amit? I guess it's the
Yeah,
same thing.
I think she's sharing a different screen. She's sharing the browser, whereas she should share the PDF.
Ma'am, I shared the PPT, ma'am. Is it visible, ma'am?
No, we can't see it. So under share screen,
Now, ma'am?
We can see a black screen. Yeah, you can check your own screen. I think
Okay, ma'am.
that way.
Sorry.
can you see it on your screen?
Yes, ma'am, it is blank. But on my desktop, there is a PPT.
So why don't you share the PPT from your desktop?
So yeah, stop sharing and then share another one of the options. Yes.
Yes, ma'am. Is it visible now, ma'am?
Yes, it is. It is.
Yes, it is.
So it is time. So
Should I ask Professor Rao because he gave this problem yesterday?
yes. And Professor Sabadikari, is she going to be around?
No, I think both of them are traveling. Like they are
I
going
see.
to a meeting.
Okay.
So let me ask Professor Rao if
Sure.
he's joining, and then we can start.
So all the students, all the participants who are going to make a presentation, it is for them. We have started live streaming on YouTube, as has been the tradition in the entire school. So if for any reason you're uncomfortable with live streaming on YouTube, please write it in the chat box. We will stop live streaming. Okay. So only if you're comfortable with live streaming, we will do it. Otherwise, we will not. Okay.
Yeah, Professor Rao is trying to log in, so he should be
Okay.
here in a minute.
Okay. So I don't know what this message is. Please move this window away from the shared application. Is it?
I have no idea either.
Okay.
Yeah, he's here. We can start now, I think.
Okay. So welcome everyone to the final session of the school, and it's a very important session because our participants get to present what they have learned, or something different, or whatever interests them. And we have two of our speakers here, and Professor Srivastav and Professor Sabadhikari could not be here for some reasons, but Dr. Kuber and Professor Rao are here. So I am sure it's going to be a learning experience for all of us here. And we have several student presentations, and this is kind of unique because students did not meet each other, right? So they would have collaborated over emails, over WhatsApp, phone, this and that. So I'm sure that was also a learning experience for everybody, right? Using technology for making such presentations. So I'm sure that was also a learning experience for all the participants. So the first group, their slides are on the screen. So Darshini is going to make a presentation on behalf of her team, and they're going to talk about real numbers and decimal expansion. Before I give it to Darshini, again, I would like to make an announcement that we are live streaming on YouTube. If you're not comfortable with that, please write to us in the chat box, and we will stop the live streaming. Okay. But it is, again, I mean, I would encourage you to let it be like this, because it's something that we are archiving, right? And it'll be there on the Isla channel, and probably will go to Association for Logic in India website at some point. So it is going to be there, and it's an important component of the school. So but it is up to you. So Darshini, you can start your presentation. We can see your slides.
Ma'am, actually,
Yes, ma'am.
Vatani, and I'll be presenting it behalf of my team, ma'am.
Can you repeat? I missed. I think my volume was low. So can you repeat it?
I'll be presenting on behalf of my team, ma'am. So she'll be the Darshini will be sharing the screen. I'll be the speaker.
Okay, wonderful. So it's again a collaborative effort. Wonderful. Please go ahead.
Good afternoon, everyone. I'm Sri Bhatani. On behalf of my team, I'm here to present on topic decimal expansion. The usage The usage of decimal system started since around 3000 BCE. Notably, Archimedes invented a decimal positional system in his sand reckoner. So it is sand reckoner. It is his work by Archimedes, in which he set out to determine an upper bound for the number of sand grains that fit in universe. Some non-mathematical ancient texts such as Vedas dating back to 1900 to 1700 BCE make use of decimals and mathematical decimal fractions. It is also said that decimal fractions were first developed and used by Chinese in the end of 4th century BCE. In this presentation, we will see proof for that every number in unit interval has a decimal expansion, and if a number has two expansions, then one is terminating and the other is non-terminating. So first we will recap some terms and theorems. Unit interval, it is represented as closed interval 0, 1. Decimal expansion, it is the number representation in base 10. So basically, base 10 is the way we assign place value to numerals. It is sometimes called the decimal system because a digit value in a number is determined by where it lies in relation to the decimal point. This base 10 system started since Indus Valley civilization. So we can say the origin of decimal counting started when we used our 10 fingers to count. Terminating decimals, it is defined as decimal number that contains a finite number of digit after the decimal point, and non-terminating decimals, it is a decimal number that continues endlessly. So we'll recap some theorems. Theorem 1, let x be a rational number whose decimal expansion terminates, then x can be expressed as p by q, where p and q are coprimes, and the prime factorization of q is of the form 2 power m, 5 power n, where m and n are non-negative integers. Theorem 2, let x is equal to p by q be a rational number such that the prime factorization of q is not of the form 2 power m, 5 power n, then x has a decimal expansion which is non-terminating, repeating. So these theorems say when a rational number can be when a rational number can be terminating and non-terminating. In case of irrational numbers, the decimal expansion does not terminate nor end with a repeating sequence. We'll go to the proof part. Every number, we are going to prove that every number in unit interval has a decimal expansion, and if a number has two expansion, then one is terminating and other is non-terminating. We are going to prove this using decimal representation theorem. The decimal representation theorem, if x is real number, when x is greater than or equal to 0 and lesser than 1, then x is equal to sum of dn by 10 power n, where for each dn is an integer between 0 and 9 for each n belongs to natural number. The theorem asserts that x has the decimal expansion 0.d1, d2, d3, etc. Let us take x belongs to 0, 1 and x is a real number. It can be represented as 0.d1, d2, d3, etc. We have digit di for every I belongs to natural number. We call the number capital Dn is equal to d1 by 10 plus d2 by 10 square and so on till dn by 10 power n. We say this sequence of digits represents a real number x if x is sum of di by 10 power I. We can also use another proof. We can denote an is equal to 10 power nx mod 10 and then solve it. This proof is for that all real numbers can be represented in decimal expansion. And now we'll continue with the decimal representation theorem. So there's a proposition. Every infinite sequence of digits 0.d1, d2, d3 represents a unique real number. X belongs to closed interval 0, 1. And x will be greater than or equal to dn and lesser than or equal to dn plus 1 by 10 power n for all n belongs to natural number. Let us start taking an arbitrary infinite sequence of digits 0.d1, d2, d3. then dn will be equal to d1 by 10 plus d2 by 10 square plus and so on till dn by 10 power n, which when we solve will be strictly lesser than 1. Also, we know that sum of non-negative numbers is also non-negative. So the supremum of capital Dn will be greater than or equal to 0 and lesser than or equal to 1. And therefore, it represents, we are going to take it as x is equal to supremum of capital Dn. As x is the supremum, then x will be greater than or equal to Dn. Let us take m belongs to natural number. If m is lesser than n, then dm minus dn will be lesser than or equal to 0. If m is greater than n, then dm minus dn will be equal to dn plus 1 by 10 power n plus 1 plus dn plus 2 by 10 power n plus 2 and so on till dm by 10 power m, which when we solve we get will be strictly less than 1 by 10 power n. So we are going to find the supremum over m. So it will become x minus dn will be lesser than or equal to 1 by 10 power n. 10 power n. So hence the proposition will be proved that every infinite sequence of digits 0.d1, d2, d3 represents a unique real number. X belongs to closed interval 0, 1. So since it is proved for all real numbers, it will be also true for the unit interval. So the first part is proved. The only numbers that have two decimal expansions are the ones that are of the form p by 2 power m and 5 power n, where p is an integer and m comma n are whole numbers. The only numbers that have non-unique representation are the ones that end either in infinite sequence of 0 or 9. For example, 1 by 2, it can be represented as 0.4999 etc. like 0.49 bar and 0.5. Clearly one is non-terminating and the other is terminating. Any questions?
Yeah. Did you tell what are digits?
No, sir.
Okay, yeah. So, for example, 11 is a digit or no?
Sir, 11 is a number. Digit?
Yeah. So, because you said expansion in terms of digits, d1, d2, d3, etc., right? So, what should be d1, d2, d3, etc.? Right?
The number place. Yes.
Yeah. So, can d1 be 1.5?
No, sir.
So you have to tell what are the possibilities for the DI. Okay, anyway, go ahead. Yeah. Okay.
So the DI will be between 0 and 9. The digits will be between 0 and 9.
Right. They are integers 0, 1, 2, 3, etc. 9. Okay?
Yes, sir.
Yeah. Okay.
Any other questions? Okay. So in this presentation, a rational number can have either a terminating decimal expansion or a non-terminating decimal expansion. That only we learned since 9th standard, we have learned a lot of theorems proving that a rational number can have either a terminating decimal expansion or a non-terminating decimal expansion. But for a rational number of form p by 2 power m and 5 power n, we can truncate the decimal expansion and say that it can have two decimal expansion, one terminating and the other non-terminating. And I'm concluding my presentation. I thank my excellent team members, Nivashni and Darshini. On behalf of my team, I thank BV Rao sir for giving us this sum and made us think a lot. I also thank all the speakers for enlightening us and the Logic India host for giving us this opportunity. Thank you. And sir, I'm BV Rao sir.
Yeah.
Sir, I'm having a doubt regarding this because when we were preparing this presentation, there was a doubt for us. Wherever we searched, all the theorems are saying that a rational number can have either a terminating decimal expansion or a non-terminating decimal expansion, sir. But
Right.
here the question was a bit contradictory.
Yeah. You see, first of all, in your definition of terminating, non-terminating, you should be a little more careful. You see, first of all, you said decimal expansion is representation, and you did not say what is representation. Okay? So you should say x equal to d1 by 10 plus d2 by 10 square plus d3 by 10 cube plus etc. etc. The infinite sum. Okay? Is called a decimal expansion where the di's are integers among 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And it is a terminating decimal expansion if dn is 0 for all n after some stage. And it is not terminating if infinitely many dn's are non-zero. Okay. So you should put it that way.
Yes, sir.
All right. And of course, a rational number may have recurrent expansion 0.1313131313, etc. That is a rational number. Okay. But you have made use of those two theorems earlier, right? So you have not shown that there are exactly two decimal expansions, right? So try to think
Yes,
about
sir.
it.
Yes, sir.
Okay. Yeah. Right.
Thank you, sir.
Are there any questions from the participants?
Excuse me, ma'am. Shall I stop sharing, ma'am?
Yes, you can. Yes. So, Amit, do you have any questions?
Not right now.
Okay.
Thanks.
Okay, so we can probably move to the next presentation, and it is on a problem in set, right? By Tipanvita. I can see.
Dipanita Bose, yeah.
Okay, so she's going to make it solo, is it?
Yes.
Okay, so Dipanvita, you can share your screen.
Oh, I would like to say, yeah, good work for all the first year students. Yeah, the first team was made of first year students. So
Okay,
they did
okay,
a,
that is why I was noticing that they have written soup of DN. So
yeah.
soup is for a set and not a number. So when they say soup DN, they are thinking of it as DN, where n is varying over all the natural numbers, right? And DIs are also varying. So yeah, that was something, and now it makes sense. They're first year students, so
Yeah.
probably they're not seen.
But they showed the courage, so that is commendable.
Yes, absolutely, absolutely.
Hello.
Dipanvita, yes, we can see your slides, and you can start presenting.
Am I audible? Like, actually, I'm not using my headphones, so I'm not sure if I'm audible.
You are audible.
Okay.
Please, I can hear you. I think others can also.
Yes. So, yeah, my name is Dipanvita, and I'm in second year of my master's from University of Delhi. And today I'm going to present on a problem which is given by IISER, which is based on a set which contains like finite sequences. So we'll talk about it. So here I'm going to talk about a result which is based on the set which contains all the finite, like it doesn't contain all the finite sequence, but it contains some finite sequences of length n greater than or equal to 0. So it also contains the sequence of length 0, which is basically an empty sequence. So basically by an empty sequence, we just mean that there's a function which is going from an empty set to any set S. So that's the empty sequence. Now the problem revolves like this. So let S be a set of finite sequences such that for every n greater than 0, there exists some sequence of length n in T. So T also contains the empty sequence, And the second assumption is, suppose there exists a sequence of length n, say x0, x1, dot, xn minus 1 in T, then for every I less than n, that means for every length I less than n, this sequence x0, x1, dot, xi minus 1 is also in T. Now, the third hypothesis says that for every sequence of length k, x0, x1, dot, xk minus 1 in T, this has this has finitely many extensions, till the next part, till the next term, which is basically denoted like this. There exist finitely many xk's such that x0, x1, dot, xk minus 1, comma, xk is in T. So this set is finite. So now basically this assumption C is basically saying that in T, for every n greater than 0, there exist only finitely many sequences of length n. Now from this three, considering these three hypotheses, we have to prove that there exists an infinite sequence, say y1, y0, y1, y2, and going on, such that for every k greater than or equal to 0, the first k terms, which is k0, y0, y1, and yk minus 1, the sequence of length k is also in T. Now, this is true for every k greater than or equal to 0. So basically, in order to prove this, we have I was working on the proof. So first of all, I had to construct a infinite sequence in some way. So for the proof, let's start with this. So we are given that T is a set of finite sequences of length n greater than or equal to 0 for every n, and T also contains the empty sequence. Now, from assumption A, we can say that for every n greater than 0, greater than or equal to 0, there exists some sequence of length n in T. Now, this implies that T is a non-empty set and it is infinite, like it contains infinitely many sequences. So now, using assumption A, we can say that there are only finitely many sequences. This would be using assumption C. We can say that there are only finitely many sequences in T of length n for every n greater than or equal to 0. So this is a typo. It should be now using assumption C. So for every integer n, we will, I'm going to define the sets Sn, which contains all the sequences, like all the finite sequences of length n, which are in T. So since for every n, there exists there exists a sequence of length n in T, we can define this Sn. So by assumption 1, this Sn will be non-empty since there exists at least one sequence of length n in T. And since Sn is finite, so therefore we can say that this set Sn will have some cardinality, say Ln, where Ln is less than or equal to 1. Now, so I'm going to now define uh, represent how this Sn looks like. So suppose Sn contains all the sequences of length 1, say y01, y02, and going till y0L1, because the length of S1 is L1. So this is the set of all sequences of length 1 in T. Now basically from this set, we have to choose that y0 which is of length 1 for sure, and it has infinitely many extensions. And this is always possible because since there exists, like for every n greater than or equal to 0, there exists some sequence of length n in T. So therefore, since there are infinitely many sequences, so for the first member, there are, and by assumptions B, we can say that for the first member, that singleton sequence is also in T. But the singleton sequence, for that, there are only finitely many choices. So there has to be some y0 which has infinitely many extensions, because we have to repeat that for every moment. So there will be, so this existence will be there. So there will be some y0 in S1 such that the sequence y0 has infinitely many extensions. Now, taking this why not, I'm going to make another set of sequences, which, yes. So now S2 is defined as the set of all sequences of length 2 in T. I think I have made a notation error here. So this y naught is not basically that particular term y naught. Y naught is varying over all the elements in all these like singleton elements in S1, which has infinitely many extensions. So from here we are going to get another sequence of length to y naught, y1 and s1, such that it has infinitely many extensions. So we have to repeat this process infinitely many times. So this is set S3, which contains sequences of length 3, say y0, y1, y21, and it is going up till y0, y1, y2, L3. So this is the set of all sequences of length 3 in T, such that the first two elements, if I consider that as a sequence of 2 elements, this is an S2, and here we have to choose that sequence which has infinitely many extensions going further. So basically from each set S1, S2, S3, I'm getting like the first element of the infinite sequence, second element of the infinite sequence, third, and so on. So now we will be defining the set Sn, which contains uh, the set of sequence, like which contains the sequences of length n. Now this, so from here, from this sequence Sn, I'm going to choose another set of like an n tuple, which is y0, y1, y2, dot 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 till yn minus 1, such that this n tuple is of length n and it has infinitely many extensions. So similarly, we can extend the sequence of sets Sn for n tending to infinity. So therefore, and I'll get at least one element in each Sn which has infinitely many extensions because of the non-emptiness property of Sn. So therefore, we can generate an infinite sequence y0, y1, y2, and so on, such that for every n greater than or equal to 1, y0, so this n tuple is an Sn. Now, since we have taken the elements in Sn in such a way that those are the elements of set T as well, that means Sn is a subset of T for every n greater than or equal to 1. So that means every sequence of length 1, 2, and so on is in T as well. But but because of the property that T also contains the empty sequence, and because of the because of our assumption um, B, which says that for every x naught, xn minus 1 in T, and for every I less than n, x naught to x, like the subsequence kind of thing is also in T, we can say that there exists an infinite sequence, which we have derived here itself. Yes, here itself. So for this infinite sequence, if I take any subsequence of length n, where n is greater than or equal to 0, we are also including 0 here because T contains an empty sequence. The sequence y0, y1 till yn minus 1, that is the sequence of length n, is also in T. And yes, so there we are proving the existence of an infinite sequence y0, y1, y2, and so on, such that for every n greater than or equal to 0, y0, the sequence of n tuple is also in T for every n greater than or equal to 0. Yes, so that's it. Hence, we are proving the theorem, and yes, so that's all. Any questions?
I can see SMS around with his mask. So if it's possible for you to talk, sir, do you have any questions? Since this is the problem proposed by you.
I think he's trying to unmute himself, but
okay, on the phone, right? Yeah.
Yeah,
so
on the phone.
Can we do it? Can we do something?
I mean, we can call him.
Okay.
We can call him and then he can talk. That's
No,
possible.
he has unmuted himself.
I'm
Okay,
in a
yes.
meeting. I cannot call. I cannot
Okay,
talk.
fine.
Sure.
I can say something. So this statement that he gave is known as Koenig's lemma, and it can be proved using compactness. Yeah, that was the purpose of giving this question.
Know it, but I first, like when I started doing the proof, I
Uh-huh.
did consider that the set is finite. So I thought there will be some X cases that this has a next extension. But then
Mhm.
when I sent the proof to sir, then he said that since the set is finite, it could be empty as well. So
Okay.
yeah, so then like within one day, I couldn't think much about it.
Yeah, I mean, I can give you a reference. Like, let me just try to share my screen for a moment, and
Stop
I
the
can
screen.
send you a reference.
Yeah.
You can stop.
Where you said that I comment, Deepanvita.
Yes, sir. Shall I start the screen share?
Yeah. Okay. So, while Amit is going to share that thing, reference and so on, let me mention one thing. Okay. You say your proof is fine, excellent. And the thing is, at some stage, you used similarly. Okay.
Oh, yes.
Somebody challenges, I cannot do that similarly.
Yes.
Therefore, it is better to say what is your plan of proof. What you have done is perfectly fine. You should say, for every n, I will get a sequence y0, y1, y2, yn in T. So that for every n, y0, y1, y2, yn is extended by the next sequence y0, y1, y2, yn plus 1.
Yes.
Okay?
Yes. Okay.
And then you should do it by induction. Suppose up to n, we have got sequences y0, y1, y0, y1, y0, y1, y2, etc., satisfying the condition. Then for n plus 1, I will do as follows. Exactly the same thing that you did. Okay? Yeah. Okay, fine. When you think similarly, absolutely, no problem.
So,
Yeah.
so the induction that we are using, we can use it like the statement that you have also shown in your class that if property is true for every n from 1 to then k, then it is true for every natural number.
Yeah.
Like you have to, yeah.
But you should be clear what you are proving by induction. Many times people say, I am proving by induction. You ask, what are you proving by induction? They do not know. Okay, it is very important because when you prove the inductive step true for n implies true for n plus 1, you should know what exactly is true for n. Okay? Yeah. Okay, fine. That's good.
Yes. Thank you so much, sir.
And Dipanvita, I have this condition that it contains an empty set, right? It turned out to be a crucial one, right?
Yes, ma'am. It
Suppose,
is actually a crucial.
suppose we drop condition that it contains an empty sequence.
Yeah.
Then what goes wrong?
Okay.
Can you have an alternate statement?
Yes, ma'am. I think in that case we have to drop the like final statement where k is greater than or equal to 0. For there we should have like for every like in the first statement itself we should start from n greater than or equal to 1 because t does not have any sequence of length 0. So length 0 means a sequence of length 0 means it has to be empty. So that is not guaranteed if we drop the empty sequence, like T contains the empty sequence. And in the last statement as well, where we are trying to prove that there exists an infinite sequence is that for every k greater than or equal to 0, this sequence of length k is in T, where there also we have to drop the equality.
Are there any other questions from participants?
Excuse me, ma'am.
Yeah.
Yes.
This is Ujjwal, ma'am. Can I ask a question to Amit, sir? I mean,
Yeah.
it's regarding this thing. Like you said, Koenig's lemma can be proved using compactness. No, in our college, in our logic course, we had a proof of compactness which came from Koenig's lemma. So here I see a double implication. Does this? I mean, I might be understanding this wrong, but does this imply that compactness and Koenig's lemma are equivalent statements?
Okay, I should think about it. I shouldn't say anything wrong. So perhaps I can email you later.
Okay, sure,
Yeah,
sir.
with the answer. I mean, I find it surprising that compactness can be proven in all conditions with just Koenig's lemma, because it is a statement about countably infinite sequence. So that, I mean, I would also like to see your proof.
Oh, my bad. We proved compactness only in the case of countable
Yes.
cases. Yes.
So that could be equivalent. Yeah.
Thank you, sir.
Yeah.
Okay. I don't think there are more questions. Dipanvita, thank you very much.
Thank you, Dipanvita. Yeah, you gave a correct proof. Yeah, except for what Professor Rao suggested.
I'll take care of it using it. Yeah.
Okay, so let us move on to the next presentation, which is on distributive lattices, I guess. So who is going to make a presentation?
Yes, ma'am. Wait a minute.
Okay, Nikhesh is going to. Okay.
1 minute, ma'am.
Sure. I think we should all appreciate the fact that Professor SMS is here. Even though he is in a meeting, he is listening to all of you. And we can't ask questions. Thank you, sir.
Ma'am, can you see?
No, I can't see.
Okay. 1 minute. It's not opening.
Are you sharing screen?
Nikesh, are you sharing your screen?
Yes, ma'am, but it's not opening. One second. It's slowly opening. I mean, the file is not opening, the PDF file. So
You can also ask one of your collaborators to open it in case you are facing difficulties.
no, sir, it's fine.
Vinita is here, I think. Yeah, Vinita.
Yeah. So do I share like?
Yeah, you can share and he will speak. That is fine.
Yeah. But actually, I just want to confirm: is it the same file that?
No, I have made a new one. That's
Okay. Actually, we have discussed some changes in the before lunch. So
yes.
Nikesh, send it in an email if you can. Yeah, that is also another possibility.
yeah, that's true. You can send it to me.
Vinita, you have to stop your YouTube live if you are talking.
No,
sir, it's
I'm
open.
not
Sir, it's open.
talking.
Sir, it's open. 1 minute. Sir, can you see?
No, Nikesh.
Can you see, sir? No?
You can't see. Oh, okay. Something is.
No?
Yeah, just a minute. Something is coming up. We can see a blank screen.
But we know you are trying to share.
You
Yes.
have to click on the thing and then share screen.
Sir, now it's coming.
No.
I mean, we know you are sharing, but we can't see anything. It's blank. Yeah, now yes.
Yeah.
Now we can see. Yes.
Now we can see. Yes.
Okay. So good afternoon, everyone, and I apologize for the delay. And I am Nikesh Kumar. I'm studying in third year in IISc Bangalore, pursuing bachelor's in mathematics. I am here to present my talk on behalf of my team, Muthu Kumar, Vinita ma'am, and me. The first, although the participants before me proved a theorem or something proposition, we will instead give some introduction to lattices and the deep theorem called Birkhoff representation theorem, and it will form the basis for the next part of the talk called the Naster-Tarski theorem by Nidhish and Chaitanya. So let us begin here. So I start with what is a lattice. That is, the lattice were not introduced in the school, so it's a new topic. So what do you mean by a lattice? A lattice is a non-empty set L with a partial order. It's essentially a poset such that for every pair of elements in the poset, there exists both supremum and infimum. So when you define a partial order, there is a supremum. They both have a common upper bound, least upper bound, and similarly they have a common greatest lower bound. That's what we mean by supremum and infimum. Now this is just the order theoretic definition of lattice. There is also an equivalent algebraic definition where lattice is just a three tuple where L, then there is a symbol called join, and there is a symbol called meet. So A join B will denote the supremum of the set A comma B. Similarly, A meets B will denote infimum of A comma B. So both the definitions of lattice are equivalent. One is the order theoretic, the next one is the algebraic definition. But in this talk, I will restrict my viewpoint to order theoretic and return to algebraic definition whenever necessary. So now let's see one example of a lattice. So if you take the set 1, 2, 3 under set of sorts, something like this, where the below one is an empty set, then 1, then the set containing only 2, then the set containing only 3, then 1, 2, 1, 3, 2, 3, then the whole set 1, 2, 3. So this is a this diagram is called as Hasse diagram. Using the partial order, we draw an arrow upwards so that the downward element is a subset. According to the definition of the partial order, it should be a subset of the element in the upper region. So the empty set is a subset of 1, then empty set is a subset of a set containing 2, similarly the set containing 3. Similarly, we can see that we have formed a diagram, which is called assay diagram, where supremum and infimum exist for each pair of elements. So that's why it's a lattice. Now we can take the set n under the partial order less than or equal to. So if you see, if you start from 1, then go to 2, then 3, 4, like that to infinity, then if you take any two elements like n1 and n2, since n is well ordered set, we can always say that there is a supremum and there is a infimum. Now the set of natural numbers dividing n ordered by the order, this order, if and only if it divides, will also form a lattice. This is a simple lattice. We can see from here that 1 divides 10, 5 divides 10, 2 divides 10, and 10 divides 10. Now 1 divides 5 also. So we have put the element 1 at the bottom point. Then 2 divides 10, 5 divides 10. Then we have not joined 2 and 5. essentially because 2 doesn't divide 5 and 5 doesn't divide 2. So this is one example. And these diagrams are named after a mathematician, German mathematician called Helmut Hasse. But he was not the first one to use, but Birkhoff popularized the use of Hasse diagrams in lattice theory. Now, if you come to real analysis, there is a very well defined notion of well ordering among the real numbers. So we can use the definition to take a closed bounded interval a comma b, where b greater than a greater than 0, and form a lattice under the less than or equal to definition ordering of real numbers. This is just the real line. You can see from A to B, it's just the y-axis, or you can say. Now, I would like to ask a very fun question to the audience. Anybody can answer. Can you make a lattice out of the rock, paper, scissor game? Like one will eliminate the other, right? So can you make a lattice? Can you make a lattice model out of it? This is the game we would have played in childhood, right? All of us would have played rock, paper, scissor.
So the rock paper scissor game is
Can
not
anybody answer?
transitive.
Okay. How? Can you tell how?
So the rock beats scissors and scissors beat paper, but rock doesn't beat paper. So
Okay.
suppose if we order them in like in according to what defeats what, like x is less than y if if y defeats x, then it becomes sort of like a triangle.
Okay, yeah, you are correct. So it doesn't make a lattice. But what if we tweak some of the axioms for a lattice? Can we make a similar structure similar to a lattice? If you tweak some axiom, and essentially what is that axiom? Or the definition for lattice, if you can change that, can you make it into a lattice? Okay, I will give the answer that it's just that if you put rock, then paper, then scissor, then rock, then paper, then a scissor, like that, it goes on infinitely. So the definition that should be only one element, and the transitiveness should be taken out of a lattice so that we can make a similar structure just like a lattice, but not a lattice. So this is just a fun application. Like you can find many more application in game theory or even in computer sciences, that there is a very table sorting like array or some sort of binary trees or something. So you can just apply the lattice theory there. Now there are many non-examples of lattices also. So one example is given here. Actually, the B is downwards, bit down than A, so bit lower than A, and D and C. So these are four elements and four elements of a set, and this is not an example of a lattice. Essentially, because D and C don't have a supremum. So we can say that it is not a lattice. Similarly, in the example, either they don't have a supremum, or any pair of every pair of elements don't have a common supremum or an infimum. So they are not considered as lattices. Now, what is a sublattice? Sublattice is essentially the same as a definition of a lattice. It is embedded in a bigger lattice. So sublattice also satisfies all the definition for a lattice and is non-empty. So here, and also another thing, if you want to know how lattice is connected to logic, we can think of this thing in propositional logic. Like A join B is supremum of A comma B can be thought of as the OR operation in propositional logic. Similarly, A meet B, which is same as infimum of A comma B, can be thought of as AND operation in propositional logic. Now I will just go through it. This relation to Boolean algebra. So the definition of a distributive lattice is that the meet and join operations will distribute over them. It is analogous to the set theoretic counterpart. A intersection B union C is the same as A intersection B union A intersection C. So it is similar, it is analogous to the set theoretic part, but instead we have meet and join. So a distributive lattice is essentially where the meet and join operations distribute over each other when applied to a tuple of 3 elements. So similarly, bounded lattice is a lattice where you can have a partial order such that for every x, for every element in the lattice, there exists L1 such that x less than or equal to L1. Similarly, for every x in L, there exists L2 such that L2 is less than or equal to x. So this is the definition of a bounded lattice. If you can make some intuition, it is similar to a bounded interval, like in a closed line. So similar, analogous to the, not exactly like that, it's like a bounded lattice. We can say that a finite closed assay diagram of a lattice is a bounded lattice. Now I think we have come to the last part.
Nikesh,
It will take 1
your
minute.
15 minutes are already over. So
Yeah.
just try to finish quickly. Okay.
I'll say only one thing.
Yeah. Okay.
Okay. So we cover what is a Boolean algebra here. So Boolean algebra is a distributive lattice where every element has a complement and there exist elements 0 and 1 with the following given properties. The complement is nothing like nothing but the not operation in the propositional logic, not A. So that is a Boolean algebra, and we give this Birkhoff's theorem. We stated that L is a non-distributive lattice if and only if M phi and N phi is a sublattice of L. So without proof we are mentioning, this is a very deep theorem, but proof is slightly lengthy. So L is a non-distributive lattice if and only if the given above figures are a sublattice or embedded into L. So this is the Birkhoff's theorem, and here are the references. Thank you. Any questions, please?
Yeah, I have a question. So can you go back to the non-examples? You also drew some hexagon. Is that really a non-example?
Yes, sir.
How exactly? If pentagon is a lattice, why is hexagon not a lattice?
No, B and A, they have a common, but A, E and D, they don't. Okay, supremum is there. But you can compare between D and D, right?
Yeah, you always
You
have a
take
common.
B and C.
Yeah, B and C. What is the supremum of B and C? It is F.
Okay.
And another question. So
okay, I will take care.
Yeah, so another question about Birkhoff representation theorem. So do you just need it as a sublattice or an induced sublattice?
A copy, induced sublattice, a copy.
Yes. So induced, the word induced is important. Otherwise, the theorem will fail.
No, but you can have any sublattice isomorphic to that be embedded into it, right?
But there could be more elements which will prevent, which can allow it to be a distributive lattice. I mean, just check some references. Yeah, the word induced is important there.
Okay. Yeah. Okay, sir. Sure.
Yeah, are there more questions from the audience?
Yes, ma'am. So, sir, this is to sir. So, what are induced sublattices?
Like the order is induced from the larger structure. Yeah, that's all. So the order relation is just there, like restricted to those 5 elements or restricted to those 6 elements, the lattice structure should look like this. That's all.
Okay.
Yeah.
So every sublattice is induced, but
no, you can have, like, you can forget about some of the relations. Yeah.
Okay.
That is also a sublattice. But
Okay.
the word induced is important.
Okay. I'm still not getting why is it important.
So,
why
for example, in N5, probably there was a relation between B and E in the original lattice. And you are forgetting about it.
Okay.
I mean,
Yes.
B and C, let's say B and
so
C.
we need not take every relation. Yes. Yes.
You have to take, induced means you have to take every relation that was present in the original lattice, provided those 2 elements are present in the sublattice. That is induced.
Oh, and if we forget, then we can say that it is
Yeah,
a
I mean, then you don't have this theorem. Yeah, then you don't have Berkhoff's representation theorem.
Okay.
Sir, we can say that there is a copy or isomorphic copy of N5 or
Yes,
N5.
isomorphic copy. That, I mean, you can embed N5 inside that in as a lattice theoretic embedding. Yeah, that is.
Okay.
Hello.
Yeah.
Yeah, I have a question about that rock paper scissor thing. So if you have like one rock, one paper, one scissor, that is not a lattice, because for each
No, I said
one you
if you
don't have.
tweak one of the definition of the lattice, you can make a similar thing like lattice, but not lattice.
Yeah, and so when you have a lattice, so you have taken just infinite copies of each of them, right? Or
where we are taking infinite copies of each other.
So it behaves like Z or R.
No, in this thing, the same element is repeating again and again. If you go rock, then there should be like scissors, paper, then paper, then you have a scissors, then you have rock, then like that it will repeat again and again. So it is like a multi-set.
So you need infinite copies, right? Or
yeah, a helix.
Yeah, infinite.
Yeah, fine. That is what I was asking. Thanks a lot.
Okay.
Okay, I think we should move on to the next presentation now.
Okay. Okay. Thank you, ma'am. Thank you for Isla 20 and the organizers and the faculty also. Thank you. And the audience and the participants for listening.
Okay, so I think the next presentation is by Chaitanya.
Yeah.
Right?
Chaitanya.
Chaitanya, you are not audible.
Nikesh, you should stop share screen.
Yes, sir.
Hello?
Yeah. I think the host can do it. Yeah, if he can't do. Yeah, okay, fine.
Yeah.
Chaitanya, you are still not audible. You could try to remove the headset and then speak. Unplug it from the computer. Yeah, that might be a better option.
Hello?
Chaitanya, we can hear you now.
Is it clear, ma'am? I'm audible, clear?
You are audible. You can share your screen.
Okay. Can you see the slides?
Yes, we can.
Okay, good afternoon, everyone. I am Chaitanya from IISER Bangalore. On behalf of my team, Nikesh, Vinita, Nidish, and Muthukumar, I'll be presenting on the topic Naster-Tarski theorem. The distributive lattices are already discussed by Nikesh, so he has introduced definition of lattice and some examples. So I'll move on with this. So in this talk, the goal is to study the proof of this theorem called the Naster-Tarski theorem and see some of its consequences. So we are going to prove if L is a complete lattice, then every order preserving self-map of L has a fixed point. So there are several terminologies like complete lattices, order preserving maps, and fixed points. So we'll just first introduce them. So let me just recall the definition of a lattice. It's a pose set in which every pair of elements has a greatest lower bound and the least upper bound. That is supremum, infimum, and supremum. So what is incomplete about this definition, or what can you say about what you can't say from this definition is that, say for example, first observation is that from this we can say any finite subset of L has a greatest lower bound and least upper bound. So what about infinite subsets if L is infinite? That we don't know, right? So to complete this definition, we demand that every subset has greatest lower bound and least upper bound. That is what we call a complete lattice. So a complete lattice is a lattice in which every subset has a greatest lower bound and least upper bound. Now, for a pose set, it is true that if every subset has greatest lower bound, then every subset has least upper bound and conversely. So actually, we can work with only one of these. Okay, we can just consider half the condition here. Now, coming to examples, so we have already seen. So if you take a finite lattice, then every subset has greatest lower bound and least upper bound. So by default, every finite lattice is complete. Now, one more example, simple example is that you take any set and consider the power set. It is also a complete lattice. For any sub-collection of this, what is the supremum? It is just the union of that collection, and the infimum is the intersection of that collection. Now, coming to the real line, so you consider any closed interval AB and consider in the usual order, that is a complete lattice. This we know from analysis that the set of reals has the least upper bound property and the greatest lower bound property, and even this is true in the case of extended reals also. Now, this is one example. So consider Nikesh has already considered this for a finite set. Now we'll consider this on the set of non-negative integers. So the lattice considered is set of non-negative integers in the divisibility relation. A is less than or equal to B if A divides B. So we'll just see what are the supremums and infimums of the corresponding subsets here. So you take any subset of the non-negative integers. Suppose it is infinite. Then what is the supremum? It is surprisingly 0 because every element divides 0. Okay, and what is the infimum? Infimum is actually 1. It is because 1 divides every non-negative integer. So unlike in the usual order, we have 0 less than 1. Here we have actually 1 less than 0 in this divisibility order. Another example is lattice of subalgebras of any algebra. Like, for example, you consider any group and consider all its subgroups. Then it is a lattice. What is the supremum here? It is just the, it is actually not the union, because union of groups need not be union of subgroups need not be a group. So the supremum is actually the group generated by the union, and infimum is actually the intersection. Now, consider a topological space, then it is actually a complete lattice. So again, the reason is tau, if you consider any topology, then it is closed under countable arbitrary unions. So supremum of any subcollection is actually the union, but what is infimum? We know that intersection of arbitrary collection of open sets need not be open. So the infimum here is actually the interior of the intersection. It is not the intersection, but interior of the intersection. And we know interior of any open, any set is open. So the interior of the intersection will be again in tau, and it is actually the infimum of that collection. And if you, instead of considering one topology, if you consider family of topologies on X, then again it is a complete lattice. It's called the lattice of all topologies on X. Again, the supremum is the topology generated by the union, and infimum is the intersection of those topologies. Okay, so we have seen some plenty of examples of complete lattices. Now, one more definition we want in that theorem was the order preserving map. It is just the generalization of the monotone map, what we consider on the real line. So a map, if you consider two posets, P with this order relation and P prime with this less than or equal to dash order relation, a map from P to P dash is called order homomorphism or order preserving map if x less than or equal to y implies f of x less than or equal to prime f of y. Another definition we want here is the definition of a fixed point. And if you take any self map of a non-empty set X, a point is called a fixed point if f of x equals x. So it doesn't move. The f doesn't move the point x. Okay. Now we'll come back to the proof of whatever we stated. So the theorem I stated was this: every self map of a complete, every order preserving self map of a complete lattice has a fixed point. This is the Naster-Tarski fixed point theorem. So the proof is simple. So start with a complete lattice and a order preserving self map of this complete lattice. Define a set A to be set of all elements in L for which this condition holds. X is less than or equal to fx. So observe that this is non-empty. Why? Because by the way, I forgot to tell one thing. Any complete lattice will have minimum and maximum element, because you consider the empty set, it will have the supremum, that is nothing but the minimum element, and empty set will have the infimum, that is nothing but the maximum element. Okay, so this is, so for the minimum element, this is already true for L. So the minimum element will be here, and so A is non-empty. Anyway, we don't need to argue non-emptiness here, because by definition, complete lattice means that every subset has supremum and infimum. So by definition of the complete lattice completeness, we have supremum of A exists in L, so we call it as A. Now the claim is we prove that this itself is a fixed point for A, fixed point for F. So by, since this less than or equal to is actually a antisymmetric relation, so it is enough to prove f of A less than or equal to A and A is less than or equal to f of A. Now A is the least upper bound of A, so is actually upper bound. So whenever x is less than or equal to A, f of x less than or equal to f of A, because f is order preserving. Now for any x in A, x is less than or equal to f of x by definition of A. So you can say that f of A is greater than or equal to x for every x in A. That means because A is the least upper bound, A will be less than or equal to f of A, because this proves that f of A is an upper bound for A. So, but A is the least upper bound, so A is less than or equal to f of A. Now, apply f again, because f is order preserving. This will imply that f of A is less than or equal to f of A. That means that f of A is in A, but A is an upper bound, so f of A is less than or equal to A. So we have A is less than or equal to f of A and f of A is less than or equal to A, and this relation is antisymmetric. So we have this claim. So this proves the theorem. Let's see some more fact about this theorem. In fact, this set of all fixed point itself is a complete lattice. In fact, complete sublattice of L. So this is one way of constructing sublattices from a lattice, but yeah, it may be finite also. So we don't know whether it will be infinite or finite, because for identity map we have the whole space itself, and when you have unique fixed point you have only finite set. So we don't know what is the structure of this set, but what is the cardinality of this set, but this is always complete. So if you take any open, you cannot have a order preserving map or a increasing map on the interval which has open interval as a set of fixed points, that you cannot have. So this gives a structure on the set of fixed points of that order preserving map. The converse is also true, and it was proved by Davis. I shall not go into the proof of this. So this actually characterizes lattices. So a lattice is complete if and only if it has a fixed point property. By a fixed point property, I mean every order preserving map has a fixed point. So here the converse is, suppose L is a lattice such that every order preserving map has a fixed point, then L is complete. So combining these two, we can say a lattice L is complete if and only if it has fixed point property. So some generalization is also true. Instead of taking one map, you consider a family of commuting order preserving maps. Then you can find a common fixed point. So the proof is similar to whatever we have discussed earlier. Instead of here, you define A to be set of all x in L such that x is less than or equal to fx for every f in that family. Then you just repeat this proof. Somewhere in this step, you actually need to use the commutativity of that family. So the proof is analogous, but with little modification. You consider A to be this. This is true for every f in the family, and in this step, you just use the commutative property of that family. So this is something more about that Tarski's fixed point theorem. Now we'll go to the consequences. So for the first consequence, we can see is every non-decreasing map, self map of a compact interval has a fixed point. Just recall the one-dimensional Brouwer fixed point theorem. That is, every continuous map from AB to AB has a fixed point. This is a simple application of intermediate value theorem. But you see here, when you have continuity, you don't actually require the order preservingness or the monotonicity. But in this, we don't really need continuity, but we require monotonicity. So it is like trade-off between these two, when we can omit continuity, but at that point you need monotonicity, and in this case you can drop in this case you can drop monotonicity, but we need stronger assumption that the map is continuous. So this is the first observation we can make from this Tarski's fixed point theorem. And the second application we have already seen, ma'am has already discussed this Schroeder-Bernstein theorem. In that, one of the key thing is to find a set satisfying this. In fact, yeah. So find given a map, given two maps F from A to B and G from B to A, we are finding a set satisfying this relation. So this after this, once we have this set, then we define some map from A to B, which is actually a bijective map from A to B, given that F and G are injective. So the proof is again, it is already done, but in this, I will just explain in this setting. Like, so the lattice considered is actually the power set of A with the inclusion relation, and the map defined is, so this is true if and only if this map has a fixed point. So that is the idea we use. So TS is defined to be this. Then you can observe that S1 subset of S2 implies P of S1 subset of P of S2. So it is order preserving. So by Tarski's fixed point theorem, you have a S in this such that P of S is S. That proves this. And this can be used to prove Schroeder-Bernstein theorem. That is already done. So let me not explain much.
Chaitanya, your time is almost up.
Yeah, I'll complete quickly, ma'am.
Yeah.
So the third application I was discussing is I plan to discuss is this. So you consider a topological space, then the derived set of any subset is actually the set of limit points of A, and the set is closed if A contains all its limit points. If A equals A prime, then A is called a perfect set. Then A is said to be scattered if only subset of A which has this property is actually the empty set. Now the result is that every closed subset of topological space is actually the disjoint union of a perfect set and a scattered set. So in the scattered set, you have points which are not limit points, but in the perfect set, every set is a limit point. But still, you can write every closed subset as a union of these two. So the proof is that you start with a closed set and define B to be this set of all S in the power set of X with this property. A intersection S prime contains S, and C you define to be the complement of B in A. So we'll claim that B is perfect and C is scattered. That will prove that A is actually B union C with this property, whatever B union of perfect set and a scattered set. So again the lattice considered is this. You consider T to be this map A intersection S prime, then it is order preserving. So there is a S in L such that A intersection S prime is S. This will actually prove that A intersection B prime is B. So this shows that B prime contains B. On the other hand, you have A is closed and B is contained in A implies B prime is contained in A prime, but A is closed, so A contains A prime. That proves that B prime is contained in B. So B is actually B prime. That means B is perfect. Now to prove that C is scattered, you consider a subset of C and such that S prime contains S. Then A intersection S prime contains S because S is contained in A. Now, by the definition of B, this says that this particular S is actually a subset of B because B is the union of all these kind of sets, all these S for which S this is satisfied. Now, B contains S as well as C also contains S, but B and C are disjoint. That means S has to be empty. So this proves that C is scattered. So if A is the union of B and C, then B is perfect and C is scattered. Yeah, that's all I wanted to say. So this is the original paper of that Davis, like the converse of Naster-Tarski's fixed point theorem, and this is the original paper, that Tarski's fixed point theorem. And these are some books where you can read Introduction to Lattice Theory. And this is one article for which I referred. I mean, these all the applications are there in this article. Like it appeared in Resonance in the year. That's all. Thank you. Any questions?
Thanks, Chaitanya. Are there any questions?
Hello.
Yes.
Yes, Chaitanya. So can you move back to the definition of scattered space?
Yeah.
Okay, so it says that a set is scattered if for every subset the set. So can you just once again explain the definition for A being scattered?
Yeah. So a scattered set is that it has every subset has a point which is not a limit point.
Okay, so A is said to be scattered if every subset
Yeah,
of S.
so it is like you start with the topological space X and you consider a subset, then you can have a subspace topology, right? In that.
Yes.
Now, in that subspace topology, now you consider the subsets of that. So every subset of that set should have a point which is not a limit point.
Okay.
Yeah. And in fact, in here I told A equal to B union C, and yeah, so B is perfect means this is closed. So the corresponding scattered set, whatever we get is actually open. So that is one observation.
Okay, I think we can move on now, and if there are any more questions for Chaitanya, maybe towards the end or later you can ask him.
Okay.
Thanks, Chaitanya.
Okay, thank you.
So I think the next.
Chaitanya, which year are you in?
Actually, I just submitted thesis. I joined as a visiting scientist in IISER Bangalore.
Okay. Yeah, good. Very clear presentation.
Thank you.
So I think the next topic is undecidability of domino problem. So who is going to make a presentation?
Ma'am, me. I'm Rupkatha Chand.
Okay. Okay, Rupkatha, we can hear you. You can share your screen and start presenting.
Thank you, ma'am. Yeah. So can you see my screen?
Yes, we can see your screen.
Just a minute. Okay. So, hello everyone. We are Aditya Thorat, Agnibho Banerjee, Divyashri CR, Harsh Patel, and myself Rupkatha Chand. We have worked upon the undecidability of the domino problem. So here we will build up the connections between two related topics and the domino problem as was thought by Wang. I mean, what Wang took up, and how Wang he took up, and the Turing machine by Alan Turing, and how they are connected, and how undecidability of the domino problem, or rather the undecidability of the Turing machine, implies the undecidability of the domino problem. We'll see that. Okay, let's get started. So first we describe the domino problem, then we describe the Turing machine, and then we establish the connections, and we'll see how they are related. Fine. So Wang tiles are the set of square tiles of unit size whose edges are colored. Two squares can be joined edge to edge only if the color at the common edge matches. How? Let's see. Yeah. So here are the domino tiles. So we can match, like, let's say, so let's say I pick up this tile and this tile. So I can match this tile to this tile only at the bottom. I mean, I can place this one only at the bottom, and thus I can match it. So the edges should have same colors. And if we are given finitely many types of Wang tiles, each type is determined by coloring of the edges, but infinitely many copies, so that we don't get into the trouble of, one thing getting exhausted. Then the domino problem asks whether the tiles can be arranged side by side to the tile of the plane. So can we cover the whole plane? If we say R2, can we cover the whole plane using these domino tiles? So this is what we plan to do if it is so possible. So how Wang conjectured that if there exists tiling of the plane by the given set of Wang tiles, then there also exists a periodic tiling of the plane with a given set of Wang tiles. Here, periodic tiling means that the tiling consists of a rectangular block repeated in all directions. So what is that? So over here, let's say for example, I consider this rectangle. I should have the top and the bottom, they should match. The left and the right should match. And I should repeat this thing over and over, and thus I'll be able to, cover the whole plane. That's the periodic tiling, what Wang means. So in fact, he proved that the first statement, which we are going to state, the first statement implies the second statement in the following. So whenever there exists the tiling of a plane with given set of Wang tiles, there also exists a periodic tiling of the plane with same set of Wang tiles. This is the first statement. And he says that this implies the domino problem is decidable. And he also proves it, and we'll see how. So suppose there exists a tiling of a plane with a given set of Wang tiles. And now we concentrate on an n cross n square block of, this some n cross n square block. And we denote all such possible n cross n square blocks as Tn. And we search for all, we make a set of all these Tn's, and we, search for a periodic tiling one by one through this set of Tn's. This set of Tn, if there exists a periodic tiling, we'll find the periodic block in some Tn. And then we stop the search and output, yes, we have found out the periodic tiling. if the given set of Wang tiles cannot tile the plane, although the first state, okay, if the given set of Wang tiles cannot tile the plane, then there must exist n such that Tn is empty for all n greater than capital N. That is, we cannot continue beyond a threshold. So I found a connection with SMS's lecture in this case. He talked about, bounded thing, like we do not continue our search beyond a certain limit. So we do not continue our search beyond this certain n. So how? Form a directed graph as follows. We will add vertices in various levels. Level 0 contains only one vertex. So imagine yourself in the XY coordinate system at the origin. So for each of the finitely many Wang tiles, add one vertex at level 1. So add one vertex. You first consider one such tile. Level 2 vertices corresponds to all 3x3 blocks which can be formed. So now you go to immediately, okay, fine. You go to some 3x3 block, and this 3x3 block should contain your tile that you started off with in your initial thing. So it should be surrounded. Level 3 vertices correspond to all 5x5 blocks and so on. How is that going on? So, okay. So imagine yourself in level 1 in here. In level 3, you should be here. Level 5, you should be here. And thus the thing grows on. That's what Wang says. And there is an edge from vertex O to all vertices of level 1. There is an edge from level 1 vertex U to level 2 vertex V. From the 3x3 square, you can go to the 5x5 square. If the 1x1 square block at U is at the center of the 3x3 block at V. So you understood that we are growing. We are moving, zooming out in some sense. In general, there's an edge from vertex U to of level I to vertex V of level I plus 1 if there I plus 1 cross I plus 1 block at V properly surrounds the I cross I block at U. I hope we understood this by now, how the thing surrounds. And these are all the edges. So yeah, this was the graph I was talking about. So 1x1, 3x3, 5x5, and then we grow. So infinity lemma now guarantees the existence of tiling, which contradicts our assumption. What was our assumption? That a given set of Wang tiles cannot tile the plane. So how is the infinity lemma thing? So we have infinite number of vertices, like right now. In each case, we are growing only finitely. Growing what? We have finite set of tiles, and we need to just a minute. Okay. There are infinitely many edges to cover, and we have only finitely many set of points. And by the pigeonhole principle, there must exist at a certain after a certain level some infinite branch such that we cannot cover all the finite things are exhausted, and still we continue. So this infinity lemma tells you that our assumption is wrong. So the given set of Wang tiles cannot tile the plane then. Now we considered this periodic tiling thing, the rectangle block getting repeated, but there also exists some aperiodic tiling. So what is periodic tiling? Periodic tiling, if you translate it via some vector v in R2, then the tiling fits onto itself, so it matches. But there are tilings which won't match if you translate, and they still they cover the whole plane. And Roger Penrose discovered his famous Penrose tilings, which are example of aperiodic tilings. So here is the thing. If you translate this a bit, like let's say in this direction, then you won't be able to match the ultimate thing with this initial pattern. This covers the whole plane still. Now we put this domino problem, the way we saw the thing, into logical terms. We try to connect it with our course, and we impose the restrictions in the language of logic. So these are our domino tiles, for example. So what are our restrictions? Our restrictions are these things should match in the horizontal way. The things should match, and in the vertical way, the things also should match. So let's say this is the A tile, this is the B tile, and what is this? A x y and B x prime y, x prime being x plus 1. So if this is x, this is x plus 1, x and y being integers. So this should hold. I mean, axy and bxy x prime y should hold, or bx prime y bxy cx prime y should hold, or cxy ax prime y should hold. Meaning, for a given xy, we should have this combination, like b lies to the right of a, or c lies to the right of b, or a lies to the right of c. We cannot have anything other than that, any other combination. Let's take the vertical thing. So in the vertical way also, if we fix a coordinate xy, then similarly, if we read this out, we will see that the b, I mean, so for some b and for some a, b should be on top of a, or c should be on top of b, or a should be on top of c. These are our restrictions we are putting in logical terms. And I mean, I traced out, like this is xy. So on the same spot, on the same xy, you cannot have more than one tile. So you cannot have a and b, or b and c, or c and a at the same time. Okay, these are the restrictions we have put. And if there exists a tiling of the plane with tiles a, b and c, then the above statement, for all x for all y, p1 xy, p2 xy, or at p3 xy, this statement must hold for all xy. And this is our definition. We saw what are these p1, p2 and p3 xy. Now we put this further in a special thing called AEA formula, which begins with for all x, there exists y for all, such that for all z, in this pattern, the statement is constructed, the formula is constructed. And this is followed by a logical combination of predicates without any quantifiers. So there should not be any, equal to sort of thing. For any given set of y tiles, we can find an AEA formula such that the set has a solution if and only if the formula is not self-contradictory. Hence, we can translate the domino problem into a problem of determining whether a formula is or is not self-contradictory. Since the domino problem is undecidable, we'll show how. It follows that the problem of determining whether a given AEA formula is or is not self-contradictory is undecidable. Okay, how the domino problem is undecidable, we'll show by constructing the connection with the Turing machine to the domino problem. Okay, now we look at the Turing machine. Here are, some basic things about Turing machine, how the thing works. So you have a tape which has the input. It's an infinite tape. The Turing machine can be in a finite set of states, like the set of states is finite, and the tape head or the scanner moves left or right, and it follows the instructions. That is, okay, this is the tape head or scanner, let's say. So this delta function, this is the transition function, and Q contains the set of states, tau contains the set of, yes.
Katha, your time is almost up. So
almost up. Okay. Okay. Fine. Fine. So I was describing the Turing machine. Then it takes some inputs and gives us some outputs. We'll see what, and it moves to the left or right depending upon the thing. And it follows algorithm. It is purely mechanical. That's given by the Church-Turing thesis. So here's how it moves. So it starts with some basic state A, moves to the right to, let's say, the state B, and changes the input 0 to 1. And that's how it continues. Ultimately, it comes to halt, stop. If it has to stop, it comes to a halt. Otherwise, it does not. This is one example schema of how the Turing machine works. The final output is this 1, 1, 1, 1, 1. Is the halting problem undecidable? We have shown that using contradiction. This was the proof, but as we are running short of time, I'll skip this. And this was how.
Why don't you give just the Turing that map which reduces this problem to that problem?
Yeah,
instead of
we are
describing.
coming.
Okay. That's much shorter, and you will be able to do it in your time.
Okay.
If it is possible.
So I'll do what? I'll do the
Just the transformation, doing reducibility function. You know, you want to reduce this problem to unsatisfiability problem or set problem or something you are doing.
we actually showed that
So
using
there is a
this
reducibility.
proof. We showed that using this proof, and we just stated the problem in here. We just stated the problem and we proved this over here in this contradiction thing. I'll go over it if we have time at the end. We'll surely go over it if we have time. So I just want to show how we go from one Turing machine thing to domino problem. So we start off with one, we have this input zeros and ones, let's say. So this is a tile, and we have two types of tiles we will construct. One is action tile and another is merging tile. So let's say we start off such that all the inputs are 0 and we are transferring it to 1. The first input to 1, and so the thing on the right, in the right hand side we write 1. We start off with this, we write 1, and oops. And in the left, as we started off with A and we had 0, we write A0. Now, if we have to move to the right, we go down, or if we have to move to the left, we go up. So as we have to go to state B and move to the right, we say B in the downside. And similarly, we have the merging tile. We'll show what is merging tile and the action tile at once. So here is the B in the next state. Here is the input of the next state, which will connect it to the next action tile. On the right hand side will be the next action tile. So it will also have the A0 in the next, like here it was A0. In the next action tile, we'll have B0. We'll see like this, A0. This was the first action tile, merging tile, second action tile, merging tile, and so on. We see that it traces the same pattern as the Turing machine does. So this would be just flipped. Let's go back to the thing. Yeah, here you see the same pattern. So we have constructed one pattern of the Wang tile from one pattern of the Turing machine. Given a Turing machine, we have constructed a Wang tile. So this was our thing. Can I present the undecidability of the Turing machine? Would you allow me, or otherwise I'll stop here?
So how much time will it take, Rupkatha?
Just 2 slides.
2 slides may take very long time, so you have to give me in minutes because there are 2 more presentations. Yes.
Okay, 5 minutes.
5 minutes. What should we do, Amit? There are 2 more presentations.
Yeah, I mean, we would like to have all the participants until the end. Yeah, so
Okay,
I think we
fine.
have given a fair
Fine.
chance to her. All
Fine.
of you guys, you should practice your talk before coming to present in front of the audience. Yeah, you should know whether you can cover that much material in 15 minutes.
Okay, sir.
So, Rupkatha, it is an enjoyable topic, really. But unfortunately, I think we will stop here.
Fine.
Okay.
Fine.
And
then.
yeah, we would have to move on to the next presentation.
Fine. Then we have connected the Turing machine problem to the domino problem, as the Turing machine problem is undecidable. So we also say that the domino problem is also undecidable. Thank you.
You can share the references if there are.
Okay. Yeah. Yes. Yes.
Yeah?
Yes.
So that people can have a look.
Oops, they do not appear over here. Somehow, like there's some glitch. So we had the
Rupkatha, you should say that since halting problem is undecidable,
yes,
and you have reduced it to
domino problem.
Domino problem is undecidable.
Yes, that's what I said. That's what I said.
Okay.
Yeah.
Oh, you are going Turing machine is undecidable. Okay, continue.
Okay. So I think thanks, Rupkatha.
Welcome.
Yeah,
And
thanks.
of course the team members. Okay, so let us move on to the next presentation, and by Anand and Anand Rao and Dhruv Bhasin. So I'm not sure who is going to make the presentation.
Hello, am I audible?
Okay. Okay.
Yeah.
Yes, you are audible.
Yeah. So I'll just present my screen.
Sure.
So can you all see my screen now?
Yes, we can.
Okay. Right. So I'll start. So most of this content is based on the mini course that Dr. Amit Kuber gave. It's based on a propositional logic, and this is an implementation of a few basic features of propositional logic in like this programming language, Julia. So basically, it started off like this. So Dhruv and I were discussing a few things regarding propositional logic, and we suddenly realized that writing a program to evaluate a propositional formula is surprisingly easy. So, and once we were done with that, we were a little more ambitious, and we got to writing a proof checker, a program that checks the propositional formula. And after that, we attempted generating propositional formulas, generating proofs for given formulas. So I'll be going through all these topics one by one in the presentation. And yeah, you can stop me if you have any questions. So if you want to have a look at the code, you can visit this link. And you can also email me later if you have any questions. Right, so before we start defining the language, we need to define the meta language. So as we defined in the lectures, we start off with negation and disjunction, and we define all the other symbols in terms of these. So according to these relations over here. So yeah, so that's that. And now we also define a language. So in this case over here, it consists of 3 symbols, P, Q, and R. And that is my language using which I build my propositional formulas. So if you remember, SL is the set of all valid, well-formed propositional formulas. So we can see a few of them over here. So you see, these are constructed using only disjunction and negation. So as you'll see, yeah, this thing has a negation, and like these are all separated by disjunctions, and they're all joined together like this. So so much for the language part of it. Once we have a language, we can and once we have formulas, we can try evaluating them. So so let's say I have an expression like this over here. F is this complicated expression over here. To evaluate it, I need to replace a given variable with a Boolean value. So here I'm replacing P with the Boolean true, and you'll see what it does. So every occurrence of P has been replaced by true over here. And yeah, here and here as well. And doing this repeatedly gives an entire string written entirely in terms of Boolean values. And this can be evaluated by the computer, and that's what I've done over here. So I have a really long expression. I plug in these Boolean values and then I evaluate it. So basically, this was not too hard to write, and I hope I've given you an overview of how this part was done. So with this in place, you can also define a few other additional symbols related to this. So you remember the double turnstile we saw in the lectures? This is basically an extension of this is basically that. So we have a set of formulas implemented as a list over here, and then we have another formula over here, and we ask if S turnstile T, and it turns out it does. So the computer returns true. And similarly, you can check if two formulas are equivalent. So we have this formula over here and this other one over here. And are they equivalent? Turns out they are. Right. So this was the basic, this was like the foundation for propositional logic. And we can also try out stuff in Hilbert style deductive calculus. So the calculus involves these 4 logical axioms, which are implemented as these functions over here. Keep in mind that they're functions. I'll return to this point later. And we have a rule of inference, only one rule of inference, which is modus ponens. And that is also implemented as code over here. And we have sequence in the deductive calculus. So the sequence have 3 rules. You can read them over here. One is I've written this the other way around, but yeah, never mind. Yeah, so these are the 3 rules for sequence, and the corresponding implementations are here in code. Okay, now with all these things in place, we have the necessary tools for verifying proofs. So a proof, if you remember, it's a list of sequence. So I have a bunch of sequence over here. This is the expression. This is the rule. And these are the arguments. So I have a list of sequence over here. So this constitutes a formal proof. And I can verify it. So let's see. Yeah, so it tells me that all the steps involving modus ponens are correct. And the overall proof is also correct. And this is what I ended up proving, given these 2 assumptions over here. So I ended up proving a formula. And this is also a pretty famous result, the one over here, showing that if you have P and its negation, then you can derive any other statement, any arbitrary statement Q using these. So let's run this over here. It's a short series of 7 arguments or so. So you have P, you have not P, both by NLA, and then you have this by LA1. Then you have you can do this by modus ponens, and then you take its counterpositive. And then since you have P implies Q and P already, you can deduce Q. And Q is any arbitrary statement in the language. So this shows that any inconsistent system, this is basically a demonstration of inconsistency. And it turns out that this proof is also correct. And then this is another short proof consisting of 3 lines. And so this shows how you can verify proofs. The only thing you need to verify actually is the modus ponens step, and which is why you can see that the output always talks about the modus ponens step and not any other step. So it may not seem like much is happening now. Like I'm running these cells and it's just telling me that the proof is correct. But as mathematicians, I guess like you can I guess like you know the relief of having a proof being checked by another machine. And I guess this sort of satisfaction can be paralleled only by like discovering like getting a computer to generate its own proofs, which is what we've done in the next section. So we have shown how to so we have attempted getting the computer to prove its own theorems. So we give it a statement and then we ask it to construct a proof, and it turns out that in some cases it does work, and it produces results surprisingly fast. So before I dive into the theory of this, I'll give a few explanatory remarks. So the theorem prover that we have built proves only tautology, so sequence of this type. But we are not losing out on anything, because if we have some sequence like this, let's say, this should be a set over here, like LaTeX doesn't render the brackets for some reason. So yeah, if we have some sequence like this, proving this is sufficient, because then we can use NLA to deduce T from this. So yeah, we are not losing out on anything, because I mean, any sequence of this type can be converted to a sequence of this type. So that is one point I wanted to emphasize. And another is, so when you're doing this on pen and paper, you have access to all possible logical axioms, and you can use, I mean, you can construct whatever logical axioms you want and use them in your proof. Hello?
Yeah, your voice was not audible in the meantime.
Yeah, I think I think I suddenly got muted in between, but
Okay,
yeah, now it's working. Yeah. So another thing is, when we are doing proofs on pen and paper, we have access to all possible logical axioms. There are on computer, obviously you can't tap into the power of all these logical axioms at once. You need to do this in a restricted way. So what you can do is, you can fix a set of results derived from logical axioms, and you can ask whether a proposition can be proved using this list T alone. Basically, can you apply modus ponens repeatedly on this list to obtain the desired proposition formula? And this is not a severe handicap, because like if you look at like most of the theorems that we tried proving in class, they were simple, consisting of like one or two expressions joined by implication and negation. So it's not too much of a handicap. Like usually the elements of SL1 are enough to to generate proofs of this. So for like for simplicity, we will be dealing with a language consisting of a single symbol S, and we will be trying to prove theorems in this language. So to do this, we have one crucial function called the proof of function. While I won't be actually showing you the code of this, I will be walking you through the general outline of the algorithm, and hopefully this will give you some intuition of how it works. So this is how it works. Like I said earlier, we have a set T of tautologies, using which we want to derive the formula phi. And so we can make another definition. We can call a propositional formula P of phi proof candidate if it's of this form. So you see, this is a bunch of nested implications. P1, P2 up till Pk are just some propositional formula, and then this series of implications concludes with phi. Phi is the propositional formula that you want to prove. So now, if you manage to somehow find proofs of P1, P2 up till Pk, then you can use modus ponens repeatedly to conclude phi. So that is the basic idea that we used. And how do we check whether P1, P2, Pk have proofs? Well, what we do is, we can call the proof of function with these as the input parameters. So we are doing recursion over here, and we have a nested series of function calls until we finally get a proof for phi. So note that this may not necessarily work. Like, I mean, a given set of P1, P2, Pk may not have a proof, and it also depends on your set T. So we are operating in a constrained region, and like if it doesn't work in this region, you'll have to expand the set T of tautologies to see if you can get a proof. So the function, so I decided to write some pseudocode over here to give you a better understanding of what the function looks like. So we won't be looking at the actual code. So it's like this. So I construct a list L of all the proof candidates of phi, and these proof candidates lie in the set T of tautologies. So a proof candidate, if you remember, it's this thing over here, like a nested set of implications ending with phi. And for every proof candidate, I decompose it into a list P1, P2 up till Pk. So these are the same P1, P2 up till Pk over here. And then I construct proofs of these P1, P2 up till Pk using the same proof of function. So I'm doing recursion over here. And so the proof of function is designed to return a proof if it exists and return the empty set otherwise. So that's what we're doing here. So we have proofs of all these P1, P2 up till Pk. These may or may not be actual proofs. Some of them might be empty sets. So if all of these are non-empty, then I know that all of these have valid proofs in T. And using those, I can apply modus ponens repeatedly to return a full proof of the formula phi that we wanted. Otherwise, I continue, I select the next candidate, and I do this whole procedure again. And if none of this works, then I just return the empty set. So that is roughly how it works. And I will demonstrate a few simple examples over here. So we have S implies not S, which was one of the exercise questions. And let's see if we can generate a proof. Right, so this is a proof. It's a 3-step proof. And you can see it over here. So we have this expression over here, derived using LA4. And then we have another expression, which happens to be the first part of this thing, derived using LA3. And then applying modus ponens to these two gives what we wanted. S implies not S. Now another example. Let's try this. Okay, so this thing is slightly longer. We wanted to prove S implies S, and then we ended up with a proof of 9 lines. So how do we know if this is correct? Well, we have a verification tool, so we'll just pass it through that. And it says all these steps are correct, and the entire formal proof is correct. So I mentioned earlier that your set T might not be powerful enough to prove this theorem, to prove the proposition you want to prove. So here's an example of where that doesn't happen. Sorry, I think I got muted again. Yeah. So right. So this is an example where the propositions in your set T are not enough to prove the one you want to prove. So you'll have to expand this set somehow to get a proof of this, and that can be computationally difficult. And like from the description alone, you might have realized that this is very computationally intensive. Producing a proof, checking a proof is fine. Like you can check a very long proof, but producing a proof is surprisingly hard. So with that, we can also approach this in a different way. So this was sort of like a directed search. Like we had a particular candidate in mind, and then we try to we try to work backward and come up with a proof for this candidate phi. But we can also do the reverse. So we have a set T of formulae. We can try to see what are all the logical consequences of this set T of formulae. So we keep applying modus ponens. These are all tautologies that we get. And then applying this repeatedly gives you a huge collection of valid formulae. And now what you can do with this collection is you can take your candidate and then screen through this entire list and see if it occurs in this list. So if it does, then you return the proof corresponding to it. Otherwise, you just say this is not powerful enough, or the number of iterations you've applied this for is insufficient to capture the proof. So I have also implemented that. So we can see this happening. So I'll run the next line. It might take around 30 seconds or so. Like it's generating all the proofs for 50 iterations, 5 iterations. And we end up with this huge list of 2,730 tautologies. And now we can check if some proofs that we want are in this list. So let's search for this. Turns out it's not there, but let's search for this. Okay, it turns out I have a proof, and I'll write it out here more clearly. Yeah, so it's the same proof that we encountered earlier. Now let's try looking for more. So what about things like this thing implies? So this is a tautology. Let's look for a proof. Yeah, turns out this thing also has a proof. So the first line is simple enough. Second line is very complicated, and the third line is by modus ponens. So this is using the, this is like producing a huge library of proofs and checking if the proof that we want is contained in the library. So both these methods I've discussed so far are not perfect. Each one has its own advantages, its own limitations. So the first algorithm, this proof of algorithm, it can get very complicated very fast. If T is huge, it might have to recurse to the entire tree before concluding that a particular tail is not promising, and it'll have to return to another. It'll have to move to the next one and do this again and again. And if T is small, it's not a problem. But when T is huge, it can take a very long time to prove things. But on the other hand, this thing over here sort of avoids that. Like we can do things sequentially and systematically and in a controlled way. We can produce new proofs up, and then we can specify the number of iterations, and we can check whether a given proof is in a library or not. But this approach is kind of blind, so as to say. Like it doesn't really have any foresight while we are applying it. Like, so we are just producing all possible tautologies, and then we are checking if the tautology that we want is in this list or not. So it's not so that way it's not directed like this one over here. But there's a possibility of combining the two and harnessing the advantages of both to build something slightly more powerful. So when we are looking for a proof of this, instead of searching directly, instead of calling the function
again. Anand, I'll just mention that your time is up. So how much more
I'll
time?
end in around 30 seconds or so.
Okay, sure.
Yeah. So instead of calling this, we can just look for the proof in this library. And so these have their advantages and disadvantages, and but both are still like capable of proving simple formulas like this. So yeah, that is pretty much it. If you have any questions, you can either ask now or you can email me later. Yeah. Thank you.
Thanks, Anand and Dhruv. Are there any questions?
Yeah, very nice presentation. Yeah, but
thank you.
Like I'm really happy to see that you guys did it in past 4 days while the school is running.
Yeah.
Yeah. You could implement all these things in one go. Yeah, that's really commendable.
Thank you.
Yeah, Anand is very good. But Julia, I don't know anything about computer languages. Julia is a language, is it?
Yeah, it is a language. Yeah, it's similar to Python, but it has some features that Python doesn't have.
Oh, I see. And does it have all the features that Python has and some more, or?
Yeah, it's more or less like that. Like it supports Unicode, and it can accomplish almost anything that Python accomplishes, and it has more.
I see. Very good. Okay.
It's not related, but it's meant for scientific programming.
Right. Okay,
yeah.
Good.
Sir, I have a question.
Yeah.
Hello.
Yeah, I have a question, but it may not be directly related. But is it related to somewhat like homotopy type theory or something like that? Because I've seen many such programming types and all.
Yeah, I mean, I'm a novice myself, but I don't really know much about homotopy type theory. But what I know is so libraries like Lean and all that, so this is just proving in propositional logic. So I don't need any fancy machinery for that. It's kind of straightforward. But when we're doing general mathematics, I guess things like homotopy type theory and stuff like that will come in handy. So this is just like proof in propositional logic. So it's quite straightforward. We have only one rule of inference, and we have a set of logical axioms. So we don't need things like that. Yeah.
Okay, thank you.
Yeah.
Are there more questions? Okay, if not.
Yeah, just to add to this homotopy type theory answer, there are automatic theorem checkers. Yeah, proof verification can be done. Generating proofs is always going to be hard, as he already demonstrated. And if you can generate proofs, then actually that would be useless, right? What will humans do? What will mathematicians do?
They can sleep
without getting any money.
Correct.
Yes.
Computer will take over.
So Dhruv says that they can analyze those proofs.
Oh.
Okay. Well, so thanks Anand and Dhruv for this excellent presentation.
Thank you.
And Let us move on to the last presentation, which is by Shashank and Prasanna.
Hello, am I audible?
Yes, Prasanna, you are audible. You can show your screen.
Uh, is my screen visible?
Yes, we can see you.
Okay, so good evening, everyone. And I'm Prasanna, and I and Shashank we made this small presentation trying to present like a monumental result about automated, like Amit sir's comment like proved to be a good segue into this. So this is basically on the uh, automated theorem proving and how automated theorem prover proved the Robbins conjecture. So yeah, uh, so so first we'll try to like caution you. This is more of a history doc than mathematics because we try to follow the proof that the automated theorem prover gave, and we were like, it is a 8,000 line proof, and we couldn't understand anything. Also, like the algorithm that the like equational prover EQP uses, it has a lot of subtle points which we tried to understand, but we couldn't. Like we are still in the process of understanding, so we won't present any pseudocodes over here. We'll try to explain basically what the Robbins conjecture is and what the theorem prover tried to prove. So now that we know what a formal proof is, so for formal proving automated proving has basically two blurry divisions: interactive theorem proving. So basically, some part we try to like like in the previous talk, they had a few rules of inferences, and then there were two approaches. One was a directed method and second was a search type method where the computer iteratively generated all the possible statements which are tautologies, and then we checked whether the R statement is in the set of statements generated. So interactive is like it is a kind of a directed method, and automated is just so it is so it is like an iterative method, but it is slightly more like it is much more like, complicated than that. So yeah, so the timeline goes as follows. So for the first time, the Presburger algorithm for additive arithmetic, where the Presburger algorithm is where the multiplication is defined as a iterative addition, and we do not need multiplication as a separate operation over fields. And this was a decidable arithmetic, and a computer in 1954 proved that sum of two evens is even in Presburger. So yeah, so Wang's procedure had generated proofs of all the results in Principia Mathematica by 1956, and then we had the first program to check validity of mathematical proofs and the construction of real numbers from rationals using Dedekind cuts, where you take so basically you take rational numbers and use Dedekind cuts to construct a real number, and first like for that you have the assumption of least upper bound property and all. So that was verified in 1968 using a proof checker like we saw last time. These are a few results which were verified in the timeline. So yeah, so this was the first instance where a proof of a theorem which was previously not known is an automated one. So previously it was the Robbins conjecture, and this proof made it the Robbins theorem, I guess. So the Robbins conjecture is that yeah, so basically we'll start with the Boolean algebra. We have already seen like the definition of Boolean algebra in the lattice distributive lattice talk. So the standard axioms for the Boolean algebra are as follows. So these are slightly different. I'll explain how. So a Boolean algebra is a set B endowed with the binary operation and a unary operation. So the property of the binary operation is that it is commutative and associative. The set has a special element of 0, such that for all elements A plus 0 is A. There is the negation that the unary operation is that another axiom about the unary operation is that negation of A, where A is any statement in B, is A itself. Another axiom is that A plus negation A, negation of A plus negation A is 0. And last statement is A plus negation of b plus negation of c is equal to negation of a plus b plus negation of a plus c. Now you'll notice here that we haven't defined uh, another binary operation. So basically what we do is instead of defining two binary operations and then seeing the De Morgan's law kind of thing. So you see, if you use you take the initial axioms of binary Boolean algebra and you use the De Morgan's law in the last axiom, then you can see that uh, the second binary operation is distributive over the first binary operation. So basically, the last statement is equivalent to the distributive law in the Boolean algebra. So basically, now here we had five axioms for Boolean algebra, and we had to assume the existence of special elements like 0 and so special element 0. So Huntington presented the axioms. So basically, so if we take a set with these three axioms, such that the set with the binary operation plus and these three axioms, that the operation is commutative, it is associative, and it follows the Huntington equation. Then these three axioms can describe the entire Boolean algebra. If you see that, so we cannot, like, I won't present a proof of this, but we can see that the last statement is true in Boolean algebra. If you just use the last law here, then you can see the so basically the equation inside looks like the right hand side, and if you solve this, you'll get negation of x plus negation of x plus x is equal to x, which is a true statement. So that we can get. So shortly after that, Herbert Robbins posed the question whether Huntington equation can be replaced with the following equation with one less occurrence of the negation operator. So basically here it has five negation operators, and here we have just 4 in the equation. So basically we are trying to reduce the axioms as much as we can. And so this was a long-standing question to prove whether all Robbins algebras are Boolean. Boolean algebras are Robbins. So all Robin algebra, like all the terms that can be described in a Robin algebra using the Robbins equation can be described in Boolean algebra, because we can see that the Robbins equation is valid in Boolean algebra. Again, we can use the last law, distributive property of the dot and of the second operator, and we can see that the Robbins equation is true in Boolean algebra. So all the statement that can be found using the Robbins equation and the commutativity and associativity of the plus operator can be formed in the Boolean algebra. So now we have to prove otherwise. The other way around, that all statements in Boolean algebra can be expressed with just these three: the associativity, commutativity, and the Robbins equation. So Robin and Huntington couldn't find a proof or a counterexample, and Tarski also got involved, but the proof was still standing. So found a condition that forces Robin algebras to be Boolean. And why we are like mentioning this condition, because it seems very natural that so any Robin's algebra with the unary operators has, like, if the unary, then it is a Boolean algebra. Then it is Boolean algebra. So yeah. So why we mentioned this is because unusually enough, so if we prove that all Robin algebras have if this is a tautology in Robin algebra, then it will be Boolean algebra. But somehow, like, this statement seems intuitive to us, but the theorem prover proceeds in a very different way. So these are a few other statements which combined with Robin algebra. So if Robin algebra having these properties, then any one of these properties will have will be a Boolean algebra. So basically, for all x plus x is X, we see that if we have like if we study Boolean algebra like in our lower classes, we know that this is true, that A plus A is A. So another is a existential condition where for all X in the set B, there exists a C where C plus X is C. So this is like the zero element condition. And third is there exists a C for all X where C plus X is C. So this is like the one element condition. So unusually enough, so again, these are very like intuitive things to assume, but somehow even the theorem, like the theorem prover doesn't even go like, so this is the lemma that the theorem prover used. So Robin algebra satisfying, so this is the lemma that the theorem prover is, yeah, sorry. So there exist C and D. So there are two constant, so there are two elements of the set B such that C plus D is C. If a Robin's algebra has these two elements in, if there exists such two elements in the Robin's algebra, then it is a Boolean algebra. So the only thing to remain to prove is that all Robin's algebra have the such elements such that C plus D is C. That there exists such elements. So yeah, so this the theorem prover proved. So yeah, it took 8 days and 30 megabytes. So it was still a very long proof. And yeah, so like previously demonstrated, it the search function in the last presentation. So it iterated through a 2730 results. So this is yeah, so basically it was very complicated. And these are a few steps, I like a few of which we could make sense of, but I don't think I will go through all of them. But if you see the so the seventh equation is the Robbins equation mentioned in this slide here. And the last equation, if we see, so n of 3x plus x plus 2x is equal to 2x. So now all in Robbins algebra, uh, all elements xy of the set B satisfy the seventh equation. And then if any x that satisfy the seventh equation, we can have n of 3x plus x plus 2x is equal to 2x. So we get C as n of 3x plus x plus n of 3 of x plus 2x to be 2x. So basically we have got two elements, C plus D, such that C plus D is equal to C. So the condition that we had over here, that any Robbins algebra satisfying there exists C and D such that C plus D is C is a Boolean algebra. So all Robbins algebra satisfy that condition. So it is a Boolean algebra. Yeah, so we have referenced the paper. So the two things that the paper talks about is in the algorithm of the proof. So I'll just briefly describe them. Was AC unification. So basically, like we saw in the last theorem prover talks, in the last step they had rules of inferences, and the rules of inferences had modus ponens in it. So in this algorithm, somehow they managed to like add associativity and commutativity in the rules of inference itself. So they weren't chosen as separate axioms that had to be like called again repeatedly, but they were in the rules of inference itself. And next was the second step of the algorithm was paramodulation and demodulation, where they presented an order of the terms such that when you go from one term to other, the left side should have a lesser number of atomic symbols than the other, and there should be less than or equal to number of negation statements than the other. So that was demodulation. And yeah, so basically with these two tools, they iteratively generated this proof, which had like 8,871 lines. So yeah, so that's it. Like yeah, I'll stop over.
Thanks, Prasanna. Are there any questions?
Yeah, very good presentation. Yeah, I mean, this aspect has to be studied by the young people. Yeah, the the connections with proof theory as well as connections with implementation and computer science related problems. Yeah, that is an important aspect necessary for this current generation of mathematics and computer science interplay. So great job.
Prasanna, where are you from?
I'm from Pune, Maharashtra.
Good place in IISER or?
No, I'm in IISER Bhopal, but okay.
Oh, I see you are in IISER Bhopal, right? Okay, fine. Yeah, okay.
Okay, thank. Sujata, you want to say something?
Yeah, just to add to what Amit was saying, like the 4-color problem was actually solved by doing proof using the computers as this proof as well, Robbins algebra. And I completely agree with you. Like in today's generation, mathematicians and computer scientists should work together and come up with checkable proofs as well as proofs can be verified through the computers. For example, the Thompson's proof of order, the theorem in algebra, that there are people from France, like 15 people. It took 15 people for 6 years to bring out a machine checkable proof of this Thompson theorem. So it takes a lot of effort as well in that sense. And I do feel the younger generation should combine and bring out more such work. There is a lot of work going on. And
yeah, of course, don't forget to learn logic.
Yeah.
For that reason.
No, exactly. You have to learn logic to understand, get a hang of all these things.
So, Professor Rao, do you want to make some concluding remarks on student presentations or this talk in specific?
I think they have worked hard and they have done a good job. I am very happy about their enthusiasm. I think they should keep up the enthusiasm. Yeah. All the best. Yes.
Professor SMS, Madam, do you want to say something?
Yeah, I want to say what Sujata was commenting. How about imagination? Is there imagination in computer science?
No, see, I'm talking
if
about
everything is, no, it's all right. What advice has been given to the student, I perfectly agree. I am not disagreeing to that. That advice is well made, and given the modern situation, but that mathematics, that charm of imagination and intuition, and this this is something that is why I am not a fan of computer. That's all.
They have imagination too.
But
They also imagine things, I'm sure.
Lot of imagination has gone into programming the computer that you are now using.
Well, okay.
Yeah, I'm sure they have imagination.
Well,
yeah.
That is a task to equip computers with imagination. Somebody had written in the chat.
Okay.
You see, Bibi, what happens is that the human mind works there, writing the program.
Of course. Good. But imagination was there. You see, imagination will never leave. You see?
No. For example, the first theorem that I learned in theoretical computer science, and it impressed me a lot, is the SAT problem, that it is NP complete.
Right.
So whatever you are doing, all the problems, it is expressed like a satisfaction problem, all the decision problems.
Right.
And then that becomes NP complete because everything can be reduced to that. And that was a fantastic theorem. So, but that is still, I would say, the theoretical theorem. Now people are talking of computer implementation. The day and time that it is, why only everybody has to, it looks has to do it. But Ramanujan machine. Oh, is there a machine called Ramanujan machine?
Where is Ramanujan machine?
No, somebody has written. No, I am not discouraging you. But I think the mathematics remains there. That kind of thinking cannot be taken away.
Sir, I think there is no contradiction with the two statements.
Yeah.
There is no contradiction.
You need everything, I suppose.
This is a consistent theory.
Yeah, it's.
I suppose we need both.
No
Actually.
contradiction whatsoever.
Anyway, I am happy that I am back to listen to be present during cheers. And I was quietly listening very faintly to the talk.
And somebody did say in the meeting, what is it we are doing? We can hear something going on.
And then I was told that there is something called earphone.
Why didn't you use a earphone network?
But I have to know the existence of an earphone. I have never proved the existence. By the way, morning I wanted to make a comment between what real and that discussion was going on. And later on a thing came to my mind that when Kohli hands over a ball to Ashwin, that is real. That's the real world. But when I ask a student, take a closed unit ball in R3, that is, there is a big difference between the two. And that should not be confused. Because a physicist definitely works with the real world. Okay? It is a different matter that it has to take the help of mathematics. In fact, they have to write quite often their results in mathematics. I don't know, I think Galileo said that nature is written in the language of mathematics. Chemistry people analyze things in laboratory, so those are real. But when you are doing mathematics, so make a difference between when I tell my class, oh, take the closed unit ball in L2 or R3. And when Kohli gives, oh, you take the ball to Ashwin, there is a fundamental difference. And in mathematics, this is only an illusion that mathematics you are doing the real world. Deep down, I mean, at the end of the day, it is abstract and it is false. It so happens that many things in the nature can be interpreted. Yeah. This is a comment which was I meant to give, but I missed it out.
Okay. Thank you, everyone. I think it brings us to the end of the 6-day school, and I think first thank goes to a few of the students who participants who had registered in the physical school. And when we could not have it during that time, they wrote us an email saying that can we have it virtually? And of course, there were a lot of question marks that were there in our minds about whether we should have it or not have it, because after all, technology is for the privileged ones, right? So we didn't want to leave out those who probably could not access internet. But we thought that still we are going to have a large pool of interested participants. So those who will not be able to attend it virtually, they can attend future such events of ALI. So with that thing, we thought of organizing it virtually. And so I thank the academic program committee, Dr. Amit Kuber and Professor SMS. Sir, I will call you Professor SM Srivastav on this formal note. So I thank both of you for bringing this exciting set of lectures. of course, along with the other team of speakers, and also coordinating with all the speakers in bringing out such a cohesive program. And I thank the speakers, of course, who are also part of the academic program committee, and Professor B.V. Rao and Professor Hemanti Sarbadhikari ma'am. And I think participants were enthusiastic, but I would say all the speakers were also really enthusiastic. Especially, Amit, I'll not count you.
Yeah,
but
I understand.
Professor SMS would probably not like this statement of mine when I put you aside in the group and not him. So, but I think the veterans were really enthusiastic, really lively. It didn't feel like a virtual meeting at all. And I'm glad we went ahead with this Zoom meeting option where it was really interactive. So it didn't, at least to me, it didn't feel like, there was any hindrance by it being virtual. And I also thank all the participants. Of course, we started off with some 170 odd people on day one, but that's how I think it happens in any such meeting. I think it's better virtually because those who are not interested could actually turn off their computer. If they had come to IISER Bhopal physically, then probably they will not run away. So they will have to stay there. So,
They will
but in the
sleep.
end, today, yeah, they can sleep, yes, but then it won't be like this. But I'm really happy that uh, from on last 3 days, especially, we had really consistent participation and enthusiastic. I mean, it was not that people are just attending for the sake of attending. They were really involved in all the lectures and discussion. Made full use of chat box as well, and also audio feature and other things. So thank you to all the participants for the enthusiasm, and also excellent student presentations. I have mentioned it before also, but I think it was a collaborative event on several fronts. You were not there together, physically present in a room, breaking your heads on these things. You were all using technology to do that. So really commendable work on that. I finally thank our, so let me finish my vote of thanks, and then there are a few things we have to do. So I thank student volunteers at IISER Bhopal, Gokul, Shrabana, Harita and Swapnil. They took lot of load of us. Really, I mean, they are still there in the background. If you can turn on your video, student volunteers, that will be nice. I'll also ask volunteers to do that right now. So our student volunteers are going to take a photograph of the gallery that they see on the screen, so that it will be for archival both for us and ALI. So if student participants, if it's possible for you to turn on your video, please do that. If not, it's fine. We would like to take as much as we can. Okay, so students, if you can take a photograph of the gallery, that will be nice.
Sorry, I was being extra shy earlier, but yeah.
There are 2 pages. Yeah, please do remember.
Yes, there are 2 pages.
One. Yeah.
Yes. Harita, who is taking the photograph?
Swapnil is taking it.
Swapnil is taking. Okay, there are 2 pages, Swapnil.
Yeah. Taken both.
Taken?
Yeah.
Okay. So
Yes.
thanks a lot. Thanks a lot, everyone. So
Well, when I asked, these people didn't switch on their videos.
yeah. Okay, and finally, I thank Sujata for being there all the time, and sending passcodes of Zoom promptly, and also we have bugged you a lot over the
She was
past few.
part of the program committee as well as the
She was there
organizing
everywhere.
committee everywhere. Yes. Without her,
Everywhere.
it was not possible, definitely.
No, not at all. Not at all. So Sujata, so Amit wanted to share the results of the
Yes.
feedback form that was shared. So Amit, you can do it now.
Yes, I will do it. I'm just
Amit, I
going to
would
do it.
you do it first, and then I would also like to say.
Yes, definitely. Yes, so these are the results of the feedback form. So participants mostly agree that they enjoyed the lectures. The pace of lectures was a bit towards the fast side, but still nobody said it was slow. That was expected. Yeah.
Nobody said it was slow.
Slow, yeah. Yeah. That was expected. Yeah. So but average is around this. So a little bit fast. Then school was interactive. Yeah, so everybody agrees with that, it seems. Then they are satisfied with the interaction with the speakers. They are not as much satisfied with the interaction with other participants, but we purposely disallowed personal messages in Zoom, because otherwise a lot of things start which are beyond our control, and then participants don't pay attention to what is going on the screen. There was some thought put into that, and except for one person, so the students mostly thought that these lectures were useful to change their perspective towards mathematics as a subject. Yeah, which is what we wanted to do. And they also think now, yeah, that the logic is a discipline of mathematics and they should take it seriously. So that question was also put.
Most of them agree.
Yes, most of them agree with that, and most of them would love to pursue logic and set theory further. So that also we are happy about. I will discuss this question a bit later. Then about the virtual school that we arranged. So this allows lot of distraction. Yeah, since you are not present in the classroom, and mixed opinion. But yeah, everybody is sitting at home. Somebody can just call you. You can get a phone, and other things can happen. Yeah, so there are lots of distractions. So there are pros and cons of every single method. We have to accept that. But they also have like mixed opinion about whether virtual schools are better opportunities for learning. Yes, there is something in the chat. Let me just see that. If yes,
all of us be invited.
Invited, yes. Just keep an eye, keep an eye on the announcements.
I would be looking forward to.
Yes. Okay, so these are the topics which participants have suggested for future schools: and forcing, model theory, fuzzy topology, automated reasons. I don't know why somebody said Gödel's completeness theorem. It was done, although not in full generality. Then intuitionistic logic and these things in depth. Axiomatic set theory, I think, is a most common topic. Then categorical logic. Then yeah, some applications of filters and ultra filters in some other subjects. Combinatorics, graph theory. Yeah, so interactions with these things. Course on forcing. Yeah, when Professor B.V. Rao was lecturing, so these forms were being filled up, and everybody was pouring on like we need a course on forcing. So proof theory, recursion theory, reasoning analogies, lattices, many valued logics, applications of model theory in set theory and topology, Banach lattices, toposes, and all these lectures are based on deterministic approach, some extension of logic and incompleteness theorem towards quantum computation. Okay, then any feedback? Yeah, so I think in general, people like this. Should happen once in a semester, especially the group projects. Yeah, so they enjoyed working on these presentations together. So yeah, lectures are informative. Then time schedule of classes could have been planned better. I don't really know, but perhaps they mean that it could be a bit slow. There are a few comments here about having some prerequisites mentioned. Yeah, like along with what we are talking, because perhaps all our courses went off. Yeah, they took off from ground after first couple of lectures. So that, yeah, that is understandable. Then so that the audience is uniform, they have some common knowledge base, and we can take it from there. And in tutorials there could have been more questions. That is what this comment says. Then a little less syllabus content in view of number of classes, but maybe for students. A follow-up school with advanced topics. Yeah, people are looking forward to next versions, and Sujata will talk something about that. So hope the school continues virtually. It's easy on the pocket while allowing us to go back to lectures on YouTube. A recording can always be done. Yeah, that is always an option. Whether you want to attend it physically or not, that's. I sincerely hope that the virtual format continues. Then it can still be more interesting. Okay, the sessions were useful, and yeah. So this vacation time, yeah. So we are aware that this was not vacation time for most of you, or at least some of you. Like 470 participants registered, but the exams were announced a bit later in their respective institutions. But there was no way that we could arrange it on Christmas Day. Yeah? People would complain about that. So therefore, we had to choose a timing which suited everybody else. And the other option was towards the end of the year, like during New Year's time. And we are allowing you to celebrate instead of attending the school. Yeah. So that was our other option, like 26th to 31st. But then we were not sure how many participants we would get. And yeah, instead of 6 days, it would be nice if it was at 8 to 10 days school, since it would give little more time to self-learn and better to understand what is taught in the class. Yes, advanced schools do have that problem. Let me check the chat once again. Oh, no. Agnivo didn't say much. Yes. So this is the feedback. So overall positive feedback, and we are all happy about this.
And also that participants took this their time to fill this form.
Fill up the form. Yes, exactly.
This was circulated this morning, right?
Yes. Like at the beginning of the second lecture.
Yeah.
And yeah, from my side, I would like to thank all the organizers for putting in the efforts for smooth conduct of the school. Yeah, you were not thanked because you did that vote of thanks.
So Aditi, do you want to say something?
Yeah, no, I sort of was I mean, just the same things that all of you said, basically, and I was really impressed by the student presentations, I have to say, at the end, given that they were listening to lectures and the fact that within 2 or 3 days they managed to prepare such presentations. But I also enjoyed all the lectures as much as I could attend. And yeah, a course on forcing generic sets, by the end, I was like, okay, I need to know more about this. But yeah, it'd be, I mean, coming from not mathematics, but from philosophy, this was very interesting segue and, connection that I could form. But yeah, and I want to thank all the participants. You were amazing, your questions, interactions. And yeah, I really wanted to, as Nikita did, thank all our organizers, the student organizers, all of you, all four of you, and also Shashank earlier for making the poster and everything. So yeah, wanted to thank everybody and the speakers, of course, for an excellent and really cohesive set of lectures. And yeah, lastly, and but not least, Sujata for, helping us all organize. So yeah, sorry, I was being a bit sort of, reticent today, but yeah, just want to thank everybody, basically. So should we have Sujata say a few things? Because, she's the one who brought us all together,
Of course. Thank you, Aditi. Yeah, actually, I wanted to say a few things. First of all, I would like to thank the participants. Without you guys, it wouldn't have happened. It's because of all your support and all your participation this happened. And I would really like to thank all the participants, especially the fact that I could see now that about still 3940 participants are still here. This is amazing. I'm really impressed. Thank you so much, all of you, for supporting us, supporting the school so much. Okay, so then I should thank the program committee members, Sir, SMS. So let me just put it this way, except for Amit, who is junior to me, all the other speakers are kind of my teachers as well. So I would like to take this opportunity to thank you all. Thank you so much for giving such wonderful talks and generate so much of interest in logic and set theory among students. Yeah, we are all really grateful to you. And thank you, Amit, for giving such wonderful talks and being there all the time and helping in the organization as well. Thank you so much. And finally, of course, I would like to thank Nikita, Aditi, and Kashyap, for agreeing to my proposal to organize this 8th Indian School of Logic and Applications in IISER, Bhopal. Thank you so much. And I would like to thank the volunteers as well. Once again, without you, the school couldn't have run so smoothly. Thank you so much. So thank you all. So there were some questions in the chat, like how would we know about the future events and how could we know about such things? So let me share a few things with you before we end. So one thing I'm really happy to share.
He's sharing something.
Did I? Okay. Let me see if I can share. Yeah. So I'm happy to share that UNESCO has appreciated all the teaching and research that has been done in logic, and they have in the 40th General Conference of UNESCO in 2019, they have announced that 14 January will be held as the World Logic Day. Okay, and so let me, yeah. So this is the UNESCO site, and they have declared that 14 January will be held at World Logic Day. And what is the specialty of this 14 January? It's the birth date of Alfred Tarski. And on this day, Gödel died in 1978. So there's two coincidences that happened on 14 January. And there was some effort and at least now that UNESCO has also kind of supported all the work from all over the world. And to celebrate this World Logic Day, there are events happening all over the world. And for example, let me give you some example of the kind of the events that are happening in Austria, Brazil, Germany, Italy, Mexico, Peru, Poland, Spain, Switzerland, United Kingdom, and more to come with. It will be happened there will be celebrations all over the world. And even Association for Logic in India, we have decided to celebrate this day with a few lectures, and you will get the information in due course. And when some of you were asking that how to get this information and how to get all this information about upcoming events. So what I would like to suggest you to do is, you all know this email address that is given to you in your Zoom link, this Logic India, org@gmail.com. So that is the Association for Logic in India email addresses. So please write to there if you want to add it. So there is a logic mailing list in India. So if you would like to get information about the happenings, about events, about logic, please do send an email there and we would add you to the logic mailing list. So by default, we will try to add all the regular participants to that mailing list. But in case we miss somebody, please do send us a mail there and we would be sure to add you to our mailing list. And finally, another event that I would like to talk about, so Association for Logic in India, there are two main events. As Sanjeeva Prasad talked about at the beginning of the school, they organize this Indian School of Logic and Applications, which this one is the eighth in the series. And on the odd years, this is the even year, on the odd years, they organize the Indian Conference on Logic and its Applications. So the next Indian Conference on Logic and Applications, which is basically the 9th Indian Conference on Logic and its Applications, will also be held virtually because of the situation. And it will be held between March 4 to 7 in 2021. So these are the dates for the next Indian Conference on Logic and its Applications. And we have a lot of invited speakers for that conference. So you can see the list there. I won't call out the names. There are a lot of invited speakers there and there are more to be added here. And then there would be some panels as well, panel discussions as well on logic and logic education and some other stuffs as well. And then there is something, if you are interested, there is a call for papers where you can submit an abstract on something that you are doing at this point. It can be something proved result, or you can submit work in progress as well. So the extended abstract must not exceed 5 pages. And there are information in this website where to submit those abstracts. But the important thing is the important dates. And the most important date for this is the submission deadline, that is January 15 of the next month. So in case you are interested, you can submit something, and of course you are all welcome to attend the conference as well. And it will be held virtual. Okay, so thank you. These are all the upcoming events that I wanted to share with you. Once again, I would like to thank you all on behalf of the Association for Logic in India. Thank you.
Nikita, you're on mute, I think. Yeah.
Thanks, Sujata. I now welcome participants to say something if you want to. I think you have heard a lot. So.
Yeah, it's time for them.
You can unmute and speak if you want to. Okay, I think we should really end the day. It's been a long day for them.
No, we would like.
But there are several.
We would like to hear something. What is the? Of course, they have given their feedback.
Feedback, and also there are several messages in the chat box.
They have
so
given a lot of things. No, that is just thank you.
Okay, I have a question about so if these things go not virtual from next year, so what happens is, like, say something is happening in our college, so even if we invite others, only like the college students only get to attend, right? Mostly because what happens is others apply and like their CVs get scanned and only some of the people get funded to go. So if this gets like non-virtual, so how would we be attending? That's the thing. Otherwise it becomes a like undeclared competition of like which college will host it, right? So because logic is not that famous, so it's a good thing right now, because like only one or two college will host, so that is fine. Yeah, that is what I want to know, because I'm not from either Bhopal.
So, Nikita, can I say something on this?
Yes, of course.
Yeah. So, Ognivo, the thing is that there have been, like, this is the eighth Isla, and this is the first one we have organized it virtually. So, all the other 7, we organize it in some place. It has been in IIT Bombay, many, like, then in Tezpur University, and in many other places all over India. So, what we do is we ensure that we have as much of student participants as possible. So first of all, there is no registration fee for the students. And even over that, we try to provide, like, try to find funding for their travel as well as their stay. So that's something we try to do to the best of our capabilities. And till now, for all the physical events, we have ensured that whoever wanted to, of course, as you already mentioned, that logic is not that popular, and we want to popularize this subject as well. So whoever kind of wanted to participate and was serious enough to come to the place wherever it is organized, we tried to help them in every way possible by provide funding for their travel as well as their stay. Okay, thank you.
Well, I am no longer in job, but when I was in job, I have organized several schools spread over the country. I mean, definitely I know Srinagar, Calicut, Tezpur, and in IISER. But now I'm retired.
And by the way, surely, I mean, even if we will go physical someday, I suppose, but then they can still put it on YouTube, no?
Yeah, and recording is not a problem.
That can still be done,
Yeah,
so that others can.
Definitely, and even if you cannot come as
even to those who cannot come physically, it shouldn't be completely out, since now the technology is there. At least YouTube.
Yes, the recording can always happen.
Yeah, ma'am, for this I want to say something. Can I say it?
Yes.
At this time, they can show their picture also, no? And they
can be seen.
Can they be seen? Vinita, can you be seen? Is it possible or they are not allowed?
It is allowed. Yeah. It
Then
depends
why
on the
don't you
participant.
why don't you switch on your camera also? It's better. Fine.
Yeah, sir. Actually, I feel that for future, if recording is done, then it will be very nice. Like when I have started like learning logic, like I have attended ICLA in 2017, I think. So like few lectures I was not able to follow, but now I learned the course, and also I'm mature enough to learn the things. So if those lectures were recorded, then I can like relearn those things. So I feel that if lectures were recorded in the future, then it will be very helpful for the students. I felt this like just.
Where do you study?
Sir, I'm a PhD student in IIT Indore.
So IIT Indore.
Yeah.
Yeah. So anyway, now for example, this was also one of my effort. I wrote a lot of books.
Yeah, that's true. Yeah.
So
Yeah, because initially when I have started, then like I had a lot of doubts, and then now things are very clear to me. So just for the beginner, it will be
because
helpful.
there is a lot of gap in this such a short time, and this is I am addressing to all the students, not only to you.
Yeah.
That in this short time one cannot give full proof.
Yeah, that's true.
So B.B. Rao has given excellent reference. Only thing is that Thomas Yek is very fat and it will frighten you. But Cunin is small. Not very small, but I can show you the two books. So,
but Thomas Deck has 3 parts: necessary, comfort, and luxury. It is for you to decide.
Is a what?
necessity, comfort, and luxury. Part 1 is necessity. You enjoy. Part 2 is comfort. It is up to you. Part 3 is luxury if you are doing research.
Yeah, you told in your lectures, sir.
So this is set theory. For set theory, this one, Thomas Eck, you see how fat it is.
I have downloaded this book, like
And
PDF I have
for
downloaded.
is this.
They can't make out how fat it is.
And soon enough, a book by me will be published by American Math Society.
Okay, sir.
But that is a different, it's not.
No, but that is more for the first introduction. I always write the introductory book.
Oh, yeah. I have read this set theory, naive set theory by Paul Holmos. That I read, like most of the things from that one. So.
Can I have can I have some discussion here? So some people are in favor of physical classrooms, some people in favor of virtual classrooms. And if we actually decide to record, will people attend? Or we have to teach to empty classrooms and then everybody will watch on YouTube?
No. Can I say something?
Yes, Vinita.
As a student, I feel like virtual is like it's good. Whenever you want, you can attend. But definitely, I feel if we attend physically, then it is very nice. Like I felt physically.
People are not writing any opinions or not speaking out. Yeah. If we start doing recordings, then why would anybody attend? Yeah, unless they have questions. If they can learn everything from others' interaction.
Yeah, then means you are saying that we don't require the classrooms itself. Like, but I don't think, at least for me, I don't think that it's very like it's better to learn in the classroom. Like,
students still come, given the chance.
But virtual is useful in the sense like you can access whenever you want, and if you don't follow something or you just forgot, then you can just see the lecture and
it's also not very easy to travel,
in that sense, sir, it's fine.
Physical classes would be more interactive. No, sir, an offline system would work
as a trip for many of us.
And for that also, like we can meet people. Like there is a difference when we are talking on the WhatsApp, and then it's a different.
I can tell you one advantage of physical classes. That is, the students together can sit in the night, discuss. After the class and learn. It is not possible on virtual classes.
And mathematical dinners and lunches.
Yes,
as well.
So those things are very important. And also, it is not that only a student and teacher should talk, communicate. A lot of students together go back and try to understand together what has been taught today. And if you are within your own circle and this, you have less inhibition. You can ask each other more questions and this. So this is one thing that will be missing. And well, of course, somebody has said that we will have a trip.
That's true. That's true. That's true. We can't deny that.
So that is, social aspect is. But I think we have socialized very well. I mean,
there were terrible lot of interruptions. So
because of internet problem.
Yeah, fortunately, my grandsons are not here.
Otherwise, we would know a lot of interactions.
Then we would have.
No, sir, due to, as I'm staying at home, that's why there were a lot of interruptions. So I would strongly prefer physical classes.
Yeah.
Actually, one should have a combination when possible.
Combination?
Have both. What they are saying, have the physical classes, but have it recorded.
Recorded for sure. Because I think webinar that we did, IIT Kanpur organized, where you gave some lectures, Puibita gave, I gave. I think that's not recorded, no?
No, that was not recorded.
See, like what somebody says here is correct. The main advantage of recordings is the possibility of going back to learn properly.
Yes. Yeah, that is a very good.
On the other hand, physical classes have a lot of advantages the other way.
Yeah,
you can interact. So you should not go.
Yeah. Amit sir, I want to say something
Yeah.
for this one. Like you said that we have to teach and like in an empty classroom. Like when I was in my masters, like NPTEL lectures are available on the YouTube, but still like there are students in like who are attending the classes. So it's not.
Right.
I feel that it's not necessary that people will prefer to attend online one if they are at like if they have the physical facility. So
I make one more offer. I have given my lectures and other things. So I think my email has been given to all of you. And if you start reading the set theory, what has gone on, and if there are doubts, you can approach me. I don't like phone calls, but over email, I will respond. But it's not that, suddenly you go today and start writing email. You study, you have a genuine doubt, you have thought over, you are not able to work out, or some concept is not getting clear. But first effort would be to make that you must have tried yourself. And normally I throw back the problem if it is okay. Excuse me.
So I would like to mention that there is one participant, Shamik Paul, who had registered.
Hello.
But I think he could not attend our Zoom sessions. So, but he was very active on YouTube.
Yes.
And he had posted several questions which actually you people had answered.
Yeah, we know him very well
A
actually.
few minutes back. I will just
Yes,
read
yes.
it out so that he is also part of this whole exercise.
You did what to him? What did you
This
say?
was the first time that I saw a proof of the first incompleteness theorem and also learned about the concept behind proving the independence of CH and AC. So I just thought I'll just say this because he has been really
Yeah, we know him very well.
participating. Yes.
तब तो वही चीज है जो हमेशा करते हैं. ठीक है. तो हम प्ले हाँ वही है. तो हम
We can wait for a couple of minutes for SMS and then just
They're waiting a couple of minutes for you to come.
हाँ ठीक है.
There are a few comments in the chat box. I think
All about you. They'll miss your jokes if it's all online and things like that.
No. Oh, who said that? Do you know that I cut a lot of jokes when I am in class?
Of course, we will not be attending. We'll miss those jokes and puns, especially made by you. All these things will be missed if they don't attend online. If they don't attend online classes, if it's just on YouTube.
No.
Recordings.
Recordings. No. But there will be there. But yeah, in my classroom, I am much more entertaining.
Small things cannot be enjoyed.
You can once one photograph, it happened that I was enthusiastically lecturing this way, that way, so on. And one participant's husband was a photographer. That lady went and talked, and he said, "Oh my God, my lecture!" And they took my permission and was going all around the room and taking pictures this way, that way. Incidentally, you will. Nowadays, I think Viveva is not that entertaining, but in his younger days, Viveva has gone away.
Yeah, he had to leave. He told
he
me
had to leave.
Yes.
Okay. Then I can talk freely. So once somebody was one research scholar was presenting something, and what he had done is that he had mugged it up. So he didn't know how second line follows from the first line and why first line.
He had just memorized the whole thing.
He had just memorized it. And he was not able to answer that why this line follows from that line. So he was saying this is correct, so that is correct. This is correct, so that is correct. Bibira was asking, but why? I said, no, this is correct, so this is correct. So Bibira gets up. Okay. At that time, Indira Gandhi was the Prime Minister. Okay. Indira is our PM. So 2x square equal to 4. Do you agree? Okay. Bibira was also very, very interesting teacher, very this. And well, actually, I have inherited a lot of things from ISI. For example, today I gave this analyze what I titled that analyzing Godel. This is not analyzing Godel, you know. In ISI those days, if we just learn a proof, that if we are given a proof and we go and say, sir, we have followed, we have read the proof. But that is not sufficient. They will ask that, how do you think the person would have got this proof? What was the thought process? So it was just learning, was just going to the proof and following each argument was not sufficient for us. We had to kind of start from the scratch, probably try to get into the mind of the person that what is a possible natural way to start from the hypothesis to here. Until and unless we can say that to our teachers, or what was the major idea, what was the major hurdle, so that this theorem is new and a new idea was needed. So what I want to tell you people is that just once you go through the proof, you can follow each and every argument. If you can follow each and every argument, and then you say, I have learned the theorem, that is not sufficient. That is not sufficient. I have an important call.
So,
Hello.
Sujata, I think we can probably conclude this session.
Yes, definitely.
So thank you again, everyone, and wish all the participants a very productive new year, and hope you remain in touch with the speakers.
Yes.
You have their email IDs, so you can always write to them with your questions and queries. And yes, so thank you, everyone.
So is it closing? We are closing now?
Yes.
Yes.
Hope to meet you all in person.
Where? Oh, in person.
Yeah.
Okay. Thank you.
Okay.
Thank you.
Bye. Bye.
Bye.
Best wishes to all of you. Happy New Year to all of you, and Merry Christmas. Enjoy your
You too.
because we have just left. We have just left you. Acha Chaitanya, I had one question. Are you from IISER Bangalore?
Chaitanya, you're muted.
You are muted.
Yes, he is. He is. Yes, he is.
What are you doing there?
He just completed his thesis, he said.
With whom?
He's not audible.
You are not audible.
Hello?
Now you are audible.
Yeah. So I did my PhD from NIT Suratkal. Recently I joined ISI as visiting scientist. Now I am with Professor Raja Rambhat.
Okay. And you could take us.
Yeah, I mean, not everything, but yeah.
You could take us.
Sorry?
Because I noticed you were giving a presentation today, right?
Sorry?
Did you present something today?
Yeah.
And then I was in a meeting, but I saw IISER Bangalore, so I was a bit curious about it.
Yeah, actually, I studied a course in lattice theory doing my MSc. So, and I actually work in dynamical systems and fixed point theory. So that is how I was interested in that.
Okay. Okay.
Okay then.
Yeah.
Okay.
Bye everybody.
Bye.
Okay.
Thank you.
Nikita and where is Swaroop?
Yeah,
No, he
Aditi,
was not here.
Yeah, she just left. Yeah.
No, Swaroop.
In Kashyap, you mean?
Kashyap.
Kashyap. So yeah, he could not join today.
He could not join today.
Yes.
Okay. Bye.
Okay, bye.
Bye.
Harita, you can end the meeting.
Yeah, sure. Okay. See you.